String theory begins with a strange possibility that the smallest things in existence may not be tiny dots at all. For more than a century, physics has worked with two great maps of reality. One map explains gravity, planets, stars, black holes, and the bending of space itself. The other explains atoms, particles, light, probability, and the strange rules that govern the very small. Each map works beautifully on its own, but when physicists try to place them on top of each other, especially inside black holes or at the birth of the universe, the lines no longer match. String theory is one attempt to redraw the map from the bottom up. It asks whether every particle, every electron, every quark, every force-carrying particle might be a different state of something even smaller, something more like a tiny vibrating thread than a point. From that one idea come nearly all the confusing parts people hear about: extra dimensions, branes, supersymmetry, parallel-looking worlds, holograms, and the question of whether the theory can ever be tested. Welcome to Mechanics of Rest. If you enjoy long, careful stories about science, history, and the ideas that changed how people see reality, a like and subscription quietly helps the channel grow. New full-story episodes are published regularly, and it is always good to know where people are listening from. So tell us your country or city in the comments. And if there is a person, topic, mystery, era, or scientific idea you would like covered next, leave that as well. For now, the first step is simple. Before strings enter the picture, there was already a problem waiting for them, a problem hidden between the two most successful theories physics had ever built. Chapter 1. Why physics needed a new door. Physics did not arrive at string theory because the old theories were weak. It arrived there because the old theories were too strong in separate directions. One theory explained the very large with unusual precision. Another explained the very small with equal success. The difficulty appeared in the narrow places where both had to speak at once. On one side stood general relativity, Albert Einstein's theory of gravity. Before Einstein, gravity had often been treated as a force pulling one object toward another, as though the sun reached across space and held the Earth in its path. Einstein changed that picture. Gravity became the shape of spacetime itself. A planet did not need an invisible rope tying it to the sun. It moved through a curved geometry, following a path shaped by mass and energy. This was a new way to think about falling, orbiting, and the large-scale structure of the universe. The Earth circled the sun because the sun changed the geometry around it. Light could bend near a massive object because the space through which it traveled was not flat in the ordinary sense. Time itself could pass at different rates depending on gravity and motion. These ideas sounded strange at first, but they became measurable. Clocks, planets, starlight, and later satellites all carried the imprint of Einstein's theory. On the other side stood quantum mechanics. It did not begin with galaxies or planets. It began with light, atoms, heat, and the stubborn behavior of matter at very small scales. Max Planck had introduced the idea that energy could come in fixed packets. Einstein used the quantum idea to explain the photoelectric effect. Niels Bohr built an early model of the atom. Werner Heisenberg, Erwin Schrödinger, Paul Dirac, and others gave the small world a language that was unlike anything ordinary experience had prepared for. In that small world, particles did not behave like tiny billiard balls moving along perfectly knowable paths. An electron could be described by probability. A measurement could change what was being measured. Certain pairs of properties could not both be known with unlimited sharpness. The theory did not always tell a physicist exactly what would happen to one particle in one event, but it told with great accuracy what patterns would appear across many events. Its predictions became some of the most precise in all of science. At first, these two great descriptions did not need to trouble each other. General relativity governed stars, galaxies, black holes, and the expansion of the universe. Quantum mechanics governed atoms, radiation, chemistry, and the particles inside matter. Each theory had its own territory, and in most ordinary situations the border between them was wide enough to ignore. A falling apple did not require quantum gravity. An electron in an atom did not require the curvature of spacetime. But nature does not keep its territories neatly separated for the convenience of human theories. There are places where gravity becomes intense and smallness becomes unavoidable. A black hole is one of those places. Its outer boundary, called the event horizon, can be enormous, but the physics that produces its deepest questions reaches towards scales where quantum behavior cannot be dismissed. The earliest universe is another such place. If the visible universe expanded from an extremely hot, dense early state, then there was a time when all the matter and energy now spread across cosmic distances occupied a condition so compressed that gravity and quantum effects could no longer be treated as strangers. The problem is not that general relativity fails in daily life. It does not. Nor is the problem that quantum mechanics fails in the laboratory. It does not. The problem is that when physicists try to combine them directly, the mathematics often becomes unstable. Gravity, treated as an ordinary quantum force, produces infinities that cannot be handled in the same clean way as the infinities that appear in other quantum field theories. The calculation loses its grip. The theory stops giving finite answers where finite answers are needed. This can be understood without equations. Imagine a description of nature that works by asking what happens at smaller and smaller distances. For ordinary matter, that method can be very powerful. A material can be divided into molecules, molecules into atoms, atoms into nuclei and electrons, nuclei into protons and neutrons, and those into quarks and gluons. Each step brings another layer of structure into view. But gravity resists this approach. At extremely tiny distances, the energy required to probe the small scale can itself curve spacetime more strongly. Trying to look more closely changes the thing being examined. At the deepest scale usually discussed in this problem, physicists speak of the Planck length. It is not a length that anyone has measured directly with a ruler or an instrument. It is a scale built from three constants of nature: the speed of light, Planck's constant, and Newton's gravitational constant. Together they mark a region where ordinary ideas of smooth spacetime and ordinary ideas of quantum fields are expected to meet their limit. The number is far smaller than an atom, far smaller than a proton, and far beyond the reach of present experiments. A strange pressure gathers there in the theory. General relativity describes spacetime as smooth, like a continuous geometry. Quantum mechanics suggests that anything physical, when examined closely enough, may not remain smooth in the same way. The two descriptions press against each other. One wants a flexible stage where gravity is geometry. The other wants a quantum world where fields fluctuate and probabilities govern the smallest events. Nothing in this conflict affects the chair, the wall, the human body, the orbit of the moon, or the chemistry of breathing. Ordinary physics continues to work because ordinary conditions do not force the two theories into their hardest meeting. The difficulty belongs to extremes: black hole interiors, the first moments of cosmic expansion, and the hidden scale where spacetime itself may need a quantum description. That is why the problem could remain invisible to most of daily life while becoming central to theoretical physics. This is where the phrase quantum gravity enters. It names the attempt to describe gravity in a way that respects quantum principles. The phrase sounds technical, but the need is simple. Gravity cannot remain separate forever if the universe contains situations where gravity and quantum behavior both matter. A complete account of nature must be able to speak about those situations without breaking its own language. Several roads have been proposed. Some approaches try to quantize spacetime itself. Some rethink geometry. Some study black holes as clues. String theory became one of the most influential roads because it changed the starting picture of a particle. Instead of treating the most basic entities as points with no size, it asked what would happen if they had a tiny extension like one-dimensional objects. That small change altered the behavior of the mathematics. A point particle is severe. It has no length, no width, no internal stretch in the ordinary picture. When interactions are calculated at a point, quantities can pile up too sharply. In string theory, the basic object is not point-like in the same way. It has extension. It can vibrate. It can be open, with two ends, or closed into a loop. The difference is not large in human terms, because the string would be far too small to see. But in the mathematics it matters. A tiny extension can soften what a point makes harsh. Instead of an interaction happening at a single dimensionless point, the process is spread along the little history of a string. The theory's early promise came partly from this smoothing effect. Calculations that looked impossible in point-particle gravity began to look different when the smallest object was no longer a point. The problem of gravity had not vanished, but its shape had changed. The most important surprise was that string theory seemed to contain gravity inside itself. Certain closed-string vibrations behaved like a particle physicists already expected in any quantum theory of gravity, the graviton. The graviton has not been detected directly, and string theory has not been experimentally confirmed as the final description of nature. Still, the appearance of a gravity-like particle inside the theory gave physicists a reason to take it seriously. Gravity did not have to be added afterward. It seemed to emerge from the same framework that described the other particles. That possibility gave string theory its new door. It was not simply a decorative idea about tiny threads. It was a way to ask whether matter, force, and gravity might share a single, deeper description. The theory did not begin as a completed answer. It began as a change in the question. Instead of asking how to force gravity into the old particle picture, physicists could ask whether the old particle picture was too narrow from the beginning. For a beginner, this is the safest place to hold the idea. String theory is not confirmed reality. It is not a proven statement that everything is made of literal strings. It is a mathematical framework that explores what happens if the most basic objects in physics are extended rather than point-like. From that proposal come vibrations, extra dimensions, branes, dualities, and many other words that can sound more confusing than the original problem. The confusion becomes easier when the order is restored. First came the success of relativity. Then came the success of quantum mechanics. Then came the recognition that both would be needed in the deepest gravitational situations. After that came the search for a new language. String theory entered as one candidate for that language, not because physicists wanted mystery, but because the familiar description of particles had reached a boundary. Before strings can make sense, though, the older particle picture has to be seen more clearly. Physics already had a way of describing electrons, quarks, light, and forces before strings appeared. That older picture was powerful, precise, and deeply tested. It was also the picture string theory would first grow out of, and in some ways move beyond. Chapter 2: Particles before strings. Before strings entered the story, physics already had a powerful way to describe the smallest known pieces of matter. That older picture did not feel incomplete at first glance. It could explain atoms, light, chemical behavior, radioactive processes, and the forces that shaped matter at scales far below ordinary sight. Its success was one reason string theory had to work so hard to be taken seriously. The word particle sounds simple. It suggests a tiny speck, a small bead, a little piece of stuff resting somewhere in space. That image is useful at the beginning, but it becomes misleading very quickly. In modern physics, an electron is not quite a bead. A photon is not a miniature pellet of light. A quark is not a colored grain sitting inside a proton. The language of particles grew out of experiments, but the deeper description became stranger than the word itself. A particle, in quantum field theory, is often understood as an excitation of a field. The field is the more basic object in that description. An electron belongs to the electron field. A photon belongs to the electromagnetic field. Quarks belong to quark fields, and gluons belong to the gluon field. When a field carries a certain amount of energy in a certain way, the result appears as a particle. The particle is what the instrument detects. The field is the quieter structure behind the event. This is one of the first places where ordinary imagination has to loosen its grip. A field is not a sheet or a liquid filling space in a literal household sense. It is a physical quantity with a value at places in spacetime, governed by rules. If the field is calm, no particle may appear. If the field is disturbed in the right way, a particle can be measured. The language is abstract, but its results are practical enough to build electronics, lasers, medical scanners, and the detectors used in particle physics. By the middle of the 20th century, physicists were learning to describe forces through particles as well. Electromagnetism could be carried by photons. The strong nuclear force, which holds quarks together inside protons and neutrons, involved gluons. The weak nuclear force, responsible for certain kinds of radioactive decay, involved heavy particles later called the W and Z bosons. Matter particles and force particles were not the same kind of thing, but they belonged to one growing grammar. The Standard Model eventually gathered this grammar into a tested framework. It included matter particles such as quarks and leptons, force carriers such as photons, gluons, and weak bosons, and later the Higgs boson, connected with the mechanism that gives certain particles mass. The Standard Model is not string theory. It does not require tiny strings or extra dimensions. It is a quantum field theory, and as a description of known non-gravitational particle physics, it has been extraordinarily successful. Still, the route toward that success was not smooth. The strong nuclear force created special difficulty. Protons and neutrons behaved as though they were made of smaller pieces, but those pieces could not be pulled out and observed alone. Experiments showed patterns of particles called hadrons, a large family including protons, neutrons, pions, and many short-lived relatives. The number of these particles grew so large that physicists sometimes called it a particle zoo. The word was informal, but the problem was real. A crowded table of particles demands order. Some physicists searched for symmetry. Some looked for deeper constituents. Murray Gell-Mann and George Zweig proposed quarks in the 1960s, offering a way to organize many hadrons as combinations of more basic objects. Quantum chromodynamics, the theory of quarks and gluons, later became the accepted theory of the strong interaction. But before that picture fully settled, another mathematical thread appeared inside the attempt to understand hadron scattering. In 1968, Gabriele Veneziano wrote down a formula that seemed to capture certain features of how strongly interacting particles scattered. He was working inside the problem of hadrons, not trying to create a theory of everything. The formula had an unusual elegance. It related different scattering channels in a way that fit the spirit of the data physicists were trying to organize. At first, it was a mathematical tool looking for a physical interpretation. That is often how physics changes shape. A formula arrives before its meaning is clear. An equation fits a pattern before anyone knows what object the equation is describing. In Venezia's case, the formula did not begin by announcing strings. It entered as an amplitude, a way of describing the probability of one scattering process leading to another. The language was technical, but the underlying question was simple. When hadrons meet and scatter, what hidden structure governs the outcome? Soon after, Yoichiro Nambu, Holger Nielsen, and Leonard Susskind recognized that the mathematics could be interpreted as the behavior of tiny vibrating strings. This was not yet the string theory later associated with quantum gravity and extra dimensions. It was an attempt to describe the strong force. A hadron could be pictured as something extended, with tension, rather than as a point-like object. The string interpretation gave the formula a body. Here, the difference between a point and a string first becomes important. A point has no length. It can be located, but it has no extension. A string has length, even if the length is unimaginably small. It can stretch, move, and vibrate. In the early hadron picture, this seemed useful because strongly interacting particles did not behave like simple, isolated dots. There appeared to be structure, tension, and patterns of excitation. The idea had a physical texture to it. A point particle gives the mind almost nothing to hold. It is a location without surface, a mark without shape. A string, even one far too small to see, allows more possibilities. It can have different modes. It can carry energy along its length. It can form different states without needing to be made of separate smaller beads. That extra internal possibility was one reason the mathematics could describe a family of particles rather than a single object. For a while, this early string picture belonged to the strong interaction. It competed with other ways of understanding hadrons, and eventually quantum chromodynamics became the stronger description of the strong force. Quarks and gluons, with their unusual confinement behavior, explained the data more successfully. String theory, as a hadron theory, seemed to lose its first intended home. That could have been the end. Many scientific ideas pass through a period of promise, fail against better evidence, and settle into history. Early string theory might have become one of those abandoned frameworks. Interesting, clever, but replaced. Yet something remained inside it that did not fit comfortably into the role it had been given. Among its mathematical states was a particle-like mode with the properties expected of a quantum particle of gravity. This was inconvenient when the theory was supposed to describe only the strong force. Gravity is far weaker than the strong interaction at particle scales. A gravity-like particle appearing inside a hadron theory looked like a flaw. But a flaw in one setting can become a clue in another. When physicists began thinking about string theory less as a theory of hadrons and more as a possible theory including gravity, the unwanted feature changed meaning. Before that turn could happen, the older particle picture had already taught an important lesson. Nature did not have to resemble ordinary objects at small scales. Matter could be field excitation. Forces could be carried by particles. Empty space could have structure through fields. Particles could be real enough to detect, yet abstract enough that the simplest mental image of tiny balls no longer worked. String theory grew inside that strange but successful world. It did not replace a childish picture with a sophisticated one. It tried to modify an already sophisticated picture whose rules had been tested deeply. This matters because many simple explanations of string theory begin too quickly, as though physicists merely decided one day that dots should become strings. The actual path was narrower. Particles had become field excitations. Hadrons had produced scattering puzzles. Veneziano's formula had appeared. Nambu, Nielsen, and Susskind had given that formula a string-like interpretation. Then the strong force purpose weakened, while the gravity clue remained. The older particle picture also explains why string theory is difficult to test. Electrons, photons, and quarks reveal themselves through experiments at accessible energies. They leave tracks, deposit energy, scatter from one another, and influence matter in measurable ways. If strings exist at something like the Planck scale, their direct size would be far beyond present instruments. What detectors would see, if anything, would not be tiny strings themselves, but particle behavior that might indirectly point back to them. This is why string theory can sound both simple and distant. The simple sentence says that particles may be different states of tiny strings. The difficult reality says that the strings belong to a mathematical framework operating at scales and energies far from direct observation. Between those two statements sits most of the confusion. The idea is easy to say. Its consequences are not easy to confirm. Particles before strings were already strange enough. They were not ordinary specks, but measured events arising from fields. Their forces were not invisible ropes, but interactions carried by other quantum objects. Their families were organized through symmetries, conservation laws, and patterns of scattering. String theory entered this world as an attempted explanation of one set of particle patterns, then slowly found another role when gravity appeared inside its mathematics. The next step is to look at the string itself with as little confusion as possible. Not a household string, not a thread made of smaller fibers, not a metaphor for music or mystery. In the theory, a string is meant to be a basic one-dimensional object, and once that single change is made, the idea of a particle begins to shift again. Chapter 3: The Smallest Thread. A string, in string theory, is not a string in the ordinary sense. It is not made of cotton, wire, fiber, or anything that could be cut into smaller strands. The word is useful because it gives the mind a first shape to hold, but the object belongs to mathematics before it belongs to ordinary imagination. It means a one-dimensional object, something with length, but no thickness in the usual picture. That single change is small in wording and large in consequence. A point particle has no extension. It is treated as having no size at all, only properties such as mass, charge, and spin. A string has extension, even if that extension is far beyond the reach of any microscope or collider. It can have different states along its length, and those states are what allow the theory to describe different particles. The safest way to begin is to remove a common misunderstanding. String theory does not say that an electron is secretly a tiny household thread floating inside space. It says that, at the deepest level of the theory, what appears to us as an electron may correspond to one possible state of a fundamental string. The particle is what the theory looks like from far away. The string is what the theory uses underneath, at a scale no present experiment can directly inspect. At ordinary scales, this difference disappears. A large object can look like a point if it is far enough away. A star, seen from Earth, may appear as a small mark of light, although it is an enormous body. A planet in a calculation may be treated as a single point if its size does not matter for the question being asked. In a similar but much deeper way, a string could look like a point particle when viewed at energies too low to reveal its extension. The string scale is one reason the theory feels so distant. In many versions of the theory, strings are associated with lengths near the Planck scale, far smaller than atoms, nuclei, or even the quarks inside protons and neutrons. This does not mean that every detail of string theory must always sit exactly at one fixed length, but it does explain the difficulty of direct observation. If the string is that small, then the instruments needed to resolve it would require energies far beyond current technology. Scale hides structure. A smooth surface may become rough under a microscope. A drop of water may become a crowd of molecules under a stronger lens. Matter that feels solid to the hand becomes mostly space and fields when examined through atomic physics. A string, if it exists in nature, would be hidden beyond many such layers, not because it is vague, but because the distance between everyday matter and that scale is so large that ordinary comparison begins to lose its use. Within the theory, strings come in two simple forms. Some are open strings, with two endpoints. Others are closed strings, shaped like loops with no ends. This distinction sounds minor, but it becomes important because open and closed strings behave differently. Their allowed motions differ, their interactions differ, and the kinds of particles they can describe are not identical. A loop can carry one set of possibilities. An open strand can carry another. An open string has endpoints, and in later versions of string theory, those endpoints may be attached to objects called branes. That idea belongs more fully to a later chapter, because branes widen the theory beyond strings alone. For now, the important point is that endpoints matter. They are not loose decorative details. They change the way a string can move and the kinds of physical behavior the mathematics permits. A closed string has no endpoints. It returns into itself. Because of this, it can move and vibrate in ways that are distinct from an open string. One of the most important features of closed strings is that their spectrum naturally includes a state with the properties expected of a graviton, the hypothetical quantum particle of gravity. This is part of the reason string theory became tied to quantum gravity. The closed loop carried a clue that the older strong force version of the theory had not been seeking. The word spectrum here means the list of possible states a string can have. A string is not only an object sitting silently in one form. In the theory, it can occupy different allowed modes. Each mode has physical properties. When seen at accessible scales, those properties can appear as different particles. One state may behave as one kind of particle, while another state behaves as another. This is where string theory begins to offer a different kind of simplicity. The world of particle physics contains many particles with different masses, charges, and spins. In the standard model, these particles are described through fields and symmetries. String theory asks whether some of this variety could come from one deeper kind of object having many possible states. Variety would not disappear, but its source would shift. The idea is easy to say too quickly, so it needs to be held carefully. A guitar string is not a good literal model, because a guitar string is made of atoms, has thickness, sits in air, and makes sound through vibration of surrounding matter. A string in string theory is not that. It is a fundamental object in a high-energy theoretical framework. It does not vibrate in air. It does not make sound. Its vibration means a mathematical state with physical consequences. Yoichiro Nambu, Holger Nielsen, and Leonard Susskind helped give early string mathematics this physical interpretation. The original context was not gravity, but the strong interaction and the behavior of hadrons. The theory's early strings were connected to patterns in scattering, where particles came in, interacted, and left in different states. Reading the mathematics as a string gave shape to a formula that had first appeared as an unexpected fit. That history matters because it keeps the idea grounded. String theory did not begin as a fantasy about hidden threads. It began inside a technical problem in particle physics. The earlier string picture was an attempt to understand why certain scattering patterns looked the way they did. Only later, after quantum chromodynamics took over the strong force role more successfully, did string theory's gravity-related features become central. A point has no internal room. A string does. Even if the room is only one-dimensional, the difference allows the theory to assign physical variety to different states of the same basic object. The string's length, tension, and allowed modes become part of the explanation. The particle, in this picture, is not a separate tiny object with its own independent essence. It is what one state of the string looks like when measured from a lower energy world. This does not mean that the standard model is thrown away. Any serious candidate theory must still reproduce what experiments already know. Electrons must behave like electrons. Photons must behave like photons. Quarks and gluons must still explain the strong interaction. A deeper theory cannot succeed by erasing the tested surface. It has to explain why the tested surface appears so accurately. That requirement makes string theory difficult. It is not enough to say that particles are strings. The theory must explain why the strings produce the right particles, the right forces, the right masses, the right symmetries, and the right low-energy world. It must also explain why the extra structure it predicts has not already been seen. This is where the simple starting idea begins to grow into the confusing architecture of the whole subject. Still, the first move remains simple. Replace a point with a tiny extended object. Let that object have allowed states. Let different states appear as different particles. Then ask what else the change requires. The moment that question is asked, the theory begins moving toward vibration, dimensions, gravity, branes, and the long argument over whether the framework describes nature or only a powerful mathematical possibility. For now, the smallest thread can be understood without all of that weight. It is a proposed fundamental object, one-dimensional rather than point-like, capable of different states, and too small to be directly seen with present tools. It is not ordinary matter. It is not a metaphor. It is a different starting point for the mathematics of particles. Once that starting point is accepted, even temporarily, the next question follows naturally. If one kind of string can appear as many kinds of particles, then the difference between those particles must come from how the string is allowed to exist. The theory's next step is to explain how a change in state becomes a change in particle identity. Chapter 4: How Vibration Becomes a Particle. Once the string has been introduced, the next confusing phrase arrives almost immediately. Different vibrations make different particles. It is the sentence many people remember from string theory, and it is also one of the easiest sentences to misunderstand. It sounds simple, but if it is taken too literally, it can become more misleading than helpful. A string in string theory is not vibrating through air. It is not making sound. It is not trembling like a thread held between two fingers. The word vibration points to something more abstract, the allowed states of a fundamental object. A string can exist in different patterns of motion and energy, and each allowed pattern has certain physical properties. When those properties are seen from the lower energy world of particles, they can appear as different kinds of particles. This is the first plain step. In ordinary particle physics, an electron is one kind of thing, a photon is another, and a quark is another. They have different masses, charges, and spins. String theory asks whether those differences might come from different states of the same deeper object. The string is not changing from one ordinary material into another. The state of the string is changing, and the particle that appears from that state changes with it. A familiar comparison can help only if it is handled carefully. A single physical system can have more than one permitted state. An atom, for example, can hold its electrons in different energy levels. When an electron changes level, the atom's behavior changes, and light may be emitted or absorbed. The atom has not become a different kind of ordinary object, yet its state matters. In string theory, the state of the string matters in an even more basic way, because the state is tied to the identity of the particle itself. The theory gives a string a set of possible modes. These modes are not chosen freely. They are constrained by the mathematics of the theory, just as a physical system in quantum mechanics has allowed states rather than any state whatever. The word allowed is important. A string cannot simply vibrate in every imaginable way. Its possible states are selected by the rules of the framework, and those rules decide what properties appear. Among those properties are mass and spin. Mass is often described as the amount of matter in an object, but in modern physics it is more subtle than that. It affects inertia, energy, and how a particle responds to fields. Spin is also not ordinary spinning like a top. It is an intrinsic quantum property, measured in fixed units, deeply connected with how particles behave. Charge describes how a particle responds to certain forces. These are not decorative labels. They are the information by which physics recognizes a particle. In string theory, an allowed state of the string can carry a certain mass, a certain spin, and certain charges. Seen from far above the string scale, that state may look like a particle with those properties. Another allowed state may have different properties, and so it appears as a different particle. The particle is not a bead attached to the string. It is the string state as it appears to a world that cannot resolve the string directly. There is a quiet shift here in the meaning of identity. In the older picture, particles are placed into families because they have different properties. In the string picture, different particle types may be related because they are different expressions of one underlying object. Variety remains, but its source changes. A zoo of separate particles becomes, at least in principle, a spectrum of states. The word spectrum is useful because physicists already use it in many places. A chemical element has a spectrum of light it can emit or absorb. A quantum system has a spectrum of energy levels. A string has a spectrum of possible states. The spectrum is the ordered collection of what the system is allowed to be. In string theory, the particle content of the theory comes from that spectrum. This does not mean the theory automatically produces the exact world we observe. That is one of the hard parts. It is possible to describe a framework in which strings have many possible states. It is much harder to show that the correct low-energy states match the particles and forces of the real universe. String theory must not merely produce particles. It must produce the right particles, with the right relationships, in a world that looks like ours. Still, the basic mechanism is clean enough to follow. Start with a fundamental string. Give it allowed quantum states. Read each state as a particle when viewed at energies too low to reveal the string's extension. The same underlying kind of object can then produce different particle appearances. This is why the phrase different vibrations make different particles survives, even though the word vibration needs care. A soft physical picture can sit inside the idea without taking over. A stretched object does not have only one way of moving. It can carry a slow, broad motion, a tighter pattern, or a more complicated shape along its length. Nothing about this comparison should be pressed too far, because a fundamental string is not a household object, but the useful part remains. Extension allows patterns, and patterns can carry information. Early string theorists found this feature in the mathematics of scattering. The old hadron problem had suggested that strongly interacting particles might lie along patterns called Regge trajectories, where spin and mass followed orderly relationships. String-like models naturally produced such relationships. That was one reason the early theory looked promising for the strong force before quantum chromodynamics became the accepted description. Then came the feature that changed the theory's future. A closed string, in its spectrum, included a massless spin-2 state. In the language of theoretical physics, that was exactly the kind of particle expected for the graviton, the hypothetical quantum carrier associated with gravity. No experiment has directly detected a graviton, yet the appearance of such a state inside string theory mattered because it suggested that gravity might not have to be forced into the theory from outside. Joel Shirk and John Schwartz took this seriously in the 1970s. Instead of treating the gravity-like state as an unwanted problem for a strong force theory, they proposed that it was a sign of the theory's real purpose. String theory, they argued, might be a framework for quantum gravity. In that reading, the feature that had once looked misplaced became central. The theory was no longer trying mainly to describe hadrons. It was trying to describe particles and gravity in one structure. The step is subtle but important. The presence of a graviton-like state does not prove that string theory describes nature. It shows that the theory naturally contains the kind of ingredient a quantum theory of gravity would need. This is different from experimental confirmation. Physics often lives for a long time with such differences, a mathematical reason to explore a theory on one side, and the absence of direct evidence on the other. For someone meeting the theory for the first time, this is where the word vibration should settle. It does not mean music. It does not mean sound. It does not mean tiny audible strings hidden inside matter. It means that the basic object has allowed states, and those states carry the properties that appear as particles. One state may look like an electron-like object. Another may look like a force carrier. A special closed string state may look like the quantum particle associated with gravity. The idea also explains why string theory became attractive to people searching for unification. If every particle is a different basic object, nature looks like a collection of separate entries. If particles are different states of one deeper object, then some of that variety may have a shared source. The theory does not remove all complexity. In many ways, it adds new kinds of complexity, but it changes where the complexity lives. That relocation matters. Instead of asking why so many particles exist as separate fundamental ingredients, string theory asks why the underlying string has the spectrum it has. Instead of asking how to attach gravity to a point-particle framework, it asks whether gravity appears naturally among closed string states. Instead of treating particle identity as the starting point, it treats particle identity as something that emerges from a deeper state. The price of this idea is high. Once strings replace points, the mathematics demands more than ordinary four-dimensional spacetime. Consistency conditions appear. Extra dimensions enter. Supersymmetry becomes important in many versions. Different types of strings and branes begin to appear. The simple phrase about vibration opens the door to a structure much larger than the phrase itself. But the first lesson can remain simple. A particle, in this theory, is what a string state looks like when the string cannot be directly seen. Different states have different physical properties. Those properties are read as different particles. Among those possible states, closed strings naturally include a gravity-like one. which is why string theory became a candidate framework for quantum gravity. Once this is clear, the next confusion becomes easier to approach. If strings are supposed to describe particles in our world, why does the theory keep speaking about more dimensions than the ones we experience? The answer does not come from fantasy. It comes from the demand that the mathematics remain consistent. Chapter 5: 10 Dimensions Without a Fantasy. Extra dimensions are often the first part of string theory that make the whole subject feel unreal. The phrase sounds as though physics has quietly opened a door into hidden places, secret worlds, or directions the body might one day step into. That is not the safest way to understand the idea. In string theory, extra dimensions begin less as fantasy and more as a demand made by the mathematics. A dimension, at the simplest level, is a direction or degree of freedom. In ordinary life, 3 dimensions of space are enough to describe where something is. A point can be left or right, forward or backward, up or down. Add time, and events can also be placed before or after one another. This gives the familiar 4-dimensional spacetime used in relativity, 3 dimensions of space and 1 of time. Nothing mysterious has been said yet. A room has width, depth, and height. A train has a position that changes over time. A falling stone has a path through space and a sequence of moments through which that path is traced. These ordinary descriptions already use dimensions, though the word itself may sound more technical than the experience. A dimension is not automatically another universe. It is a way something can vary. String theory keeps the familiar dimensions, but in many versions it cannot stop there. The mathematics of superstring theory becomes consistent in 10 spacetime dimensions. That means 9 dimensions of space and 1 of time. In M theory, the related larger framework introduced during the 1990s, the number becomes 11 spacetime dimensions. These numbers are not decorative. They are not chosen because they sound strange. They appear because the theory's internal rules work cleanly only under certain dimensional conditions. The first question is obvious. If the theory needs more dimensions, why are only 3 dimensions of space visible? The usual answer is that the extra spatial dimensions are compact. They are not spread out in the same open way as left-right, forward, backward, and up-down. They are curled, folded, or shaped at scales so small that ordinary motion never reveals them. The word curled is only a starting picture, but it is useful enough if it is not taken too literally. A small example can help without becoming the theory itself. A long cable seen from far away may look like a one-dimensional line. Something can move along its length, and from a distance, the circular direction around the cable is invisible, seen closely. However, the cable's surface has another direction, around its thickness. That second direction was always there, but it was too small to matter from far away. Compact dimensions in string theory are far more abstract than a cable's surface. Yet the lesson is similar. A direction can exist and still be hidden by scale. Scale is doing much of the work. The human body moves through large, open dimensions. A person can walk across a room, climb stairs, turn a corner, or wait for a moment to pass. Compact dimensions, if they exist in the string theory framework, would not be available in that ordinary way. They would be too small, too tightly shaped, and too deeply woven into the structure of the theory. They would affect physics not by becoming visible streets, but by changing which particles and forces appear. This is the important correction. Extra dimensions in string theory are not usually imagined as places where ordinary objects are secretly moving. They are part of the structure that determines the allowed behavior of strings. Since strings can move and vibrate through the full dimensional setting of the theory, the shape of the extra dimensions affects the possible string states. Those states, viewed from the lower energy world, become particle properties. In this way, geometry becomes part of particle physics. The need for extra dimensions came from mathematical consistency. Early versions of bosonic string theory required 26 spacetime dimensions, but that theory also had serious physical problems, including a particle called a tachyon in its spectrum and no built-in fermions like electrons or quarks. Superstring theory, which includes supersymmetry on the string worldsheet, reduced the required number to 10 spacetime dimensions and became physically more promising. Even then, the extra 6 spatial dimensions had to be handled carefully. For a beginner, the phrase 10 dimensions should not be allowed to carry too much theatrical weight. It means that the equations of the theory are naturally written in a spacetime with 10 total directions. Counting time. 4 of these correspond to the large spacetime we experience. 6 must be hidden or compactified if the theory is to resemble the world around us. The question is not whether anyone can visit them. The question is what shape they have and what that shape does to physics. A compact dimension has no need to look like a circle, though the circle is the easiest teaching image. In more serious string theory, the hidden dimensions may form complicated mathematical spaces. These spaces can have twists, holes, cycles, and geometric features that affect how strings behave. A string moving through such a shape is not merely traveling through emptiness. It is constrained by the structure of the space itself. This is where the theory begins to connect size with identity. The properties of a particle in 4-dimensional physics may depend on how a string moves through dimensions that are not directly visible. The mass of a state, the type of charge it carries, and the symmetries it obeys can all be influenced by compact geometry. A hidden shape can leave visible fingerprints, not as a picture in the sky or a doorway in a wall, but as the pattern of physics itself. The idea is not entirely without older roots. In the early 20th century, Theodore Kaluza and Oscar Klein explored the possibility that an extra spatial dimension could help unite gravity and electromagnetism. Their theory was not modern string theory, but it introduced a lasting thought. A dimension too small to see might still influence the forces observed in the larger world. String theory inherited this kind of thinking and made it far more elaborate. There is a careful distinction to make. Saying that a theory uses extra dimensions is not the same as saying those dimensions have been observed. The extra dimensions of string theory remain theoretical. They are part of a candidate framework that may or may not describe nature. Physicists study them because the mathematics of the framework requires them and because their shapes may help explain features of particle physics. Observation has not yet confirmed that such compact dimensions exist. This is why extra dimensions sit in the middle of string theory's promise and its difficulty. On one side, they give the theory enough room to produce rich particle behavior. On the other side, they create many choices. If the hidden dimensions can have many possible shapes, the theory may allow many possible low-energy worlds. That makes prediction harder. A powerful framework can become difficult to connect uniquely to the world that experiments actually observe. A quiet way to hold the issue is this. Extra dimensions are not added to make the theory more mysterious. They are required to keep the theory from contradicting itself. Once they are required, they must be hidden from ordinary experience. Once they are hidden, their shape becomes important. Once their shape becomes important, the theory faces the challenge of explaining why one shape, or one family of shapes, should correspond to the universe that exists. The body knows only the large directions. A hand reaches through width. height, and depth. A step crosses one part of a floor to another. A clock marks time as the motion continues. Compact dimensions, if they exist, would not announce themselves to that scale. They would be folded into the hidden grammar of particles, too small to walk through, yet possibly large enough in consequence to decide what kinds of particles appear at all. This makes the word dimension less exotic and more demanding. It is not a magic location. It is part of a physical description. More dimensions mean more possible ways for strings to move, and more possible ways for their states to be arranged. The extra directions may be invisible, but they are not irrelevant inside the theory. They are part of the machinery that turns strings into the particle world. The reason this matters will become clearer when the hidden dimensions are given shape. A compact dimension is one thing if it is only a simple circle. It is another if 6 hidden dimensions form a complicated space whose geometry affects every string state passing through it. String theory does not merely say that extra dimensions exist inside the mathematics. It asks what their hidden shape must be. That question leads naturally to one of the most important ideas in the theory. If the extra dimensions are real within the framework, then the shape of those dimensions may decide what physics looks like at ordinary scales. The next step is not to imagine hidden worlds, but to understand hidden geometry. Chapter 6. The shape hidden inside space. Once extra dimensions enter string theory, the next question is no longer only how many there are. The harder question is what shape they have. A dimension is a direction or degree of freedom, but a direction does not exist in isolation. It belongs to a space, and the space can be flat, curved, open, closed, simple, or folded into forms that ordinary imagination cannot easily hold. In everyday life, the shape of space feels obvious because the large dimensions are familiar. A room has corners, a road has length, a hill has slope, the surface of the earth curves, though locally it may feel flat beneath the feet. Geometry, in ordinary experience, tells objects where they can move and how paths behave. A marble rolling across a table follows one kind of path. A satellite moving around Earth follows another because the larger geometry and gravity are different. String theory extends that old lesson into a hidden region. If the theory needs 6 extra spatial dimensions beyond the 3 large ones, then those 6 dimensions cannot merely exist as blank labels. They must have structure. They must be arranged in some way. Their shape affects how strings can move, how they can vibrate, and what states are allowed. A hidden geometry, in this framework, becomes a quiet source of visible physics. This process is called compactification. The word sounds technical, but the first idea is plain. A dimension is compact if it closes back on itself or is limited in extent, so that movement through it does not continue forever in an open line. A circle is the simplest compact shape. Moving around it eventually returns to the starting point. A sphere is also compact. Its surface has no edge, yet it does not spread outward without limit. The extra dimensions of string theory are usually treated as compact in a far more complex way. They are not merely 6 tiny circles placed beside ordinary space. They may form a single higher dimensional shape with its own curves, holes, and internal patterns. This shape would be too small to see directly, but it would still influence the allowed behavior of strings. The hidden part of space would not be an empty storage room. It would be part of the rulebook. A small direction can be hard to notice. A thread seen from far away looks like a line, though something tiny could move around its thickness. A sheet of paper looks two-dimensional in many calculations, though it has a thin edge. These examples are imperfect, but they point toward the same lesson. Scale can conceal a dimension without making it meaningless. In string theory, compact dimensions are hidden not because they are unreal inside the mathematics, but because their size and shape keep them outside ordinary motion. The more serious shapes used in string theory are often called Calabi-Yau manifolds. The name comes from Eugenio Calabi, who proposed a certain kind of mathematical space, and Yau, who proved the existence of spaces with the required properties. These manifolds became important because they allowed extra dimensions to be compactified while preserving features needed by superstring theory. They offered a way for a 10-dimensional theory to appear at accessible scales, like a world with 3 large dimensions of space and 1 of time. A Calabi-Yau shape cannot be pictured accurately as a familiar object. The colorful images often shown in books and documentaries are projections, slices, or artistic renderings of something higher dimensional. They can be useful, but they should not be mistaken for photographs. The real object is mathematical. It has properties that can be studied through geometry, topology, and algebra, not through ordinary sight. Still, the reason such a shape matters can be stated simply. Strings do not only move through the large dimensions. In the full theory, they also feel the compact dimensions. The possible ways a string can wrap around hidden cycles, move through hidden curves, or settle into allowed states depend on the geometry of those dimensions. When the theory is viewed from the lower dimensional world, those hidden motions can appear as particle properties. Shape becomes physics. This is one of the most important turns in the subject. In ordinary thinking, a particle's properties may seem to belong only to the particle itself. An electron has its charge. A quark has its color charge. A photon has no rest mass. String theory suggests that at least some properties may come from how fundamental strings behave inside a larger geometry. The visible particle may carry information about a hidden shape it cannot reveal directly. This idea gives string theory some of its richness. It also gives the theory one of its greatest difficulties. There is not just one possible compact shape. There may be many. Different compactifications can lead to different particles, different forces, different constants, and different low-energy physics. The hidden geometry becomes a source of variety, and that variety is both a tool and a problem. If only one compact shape were mathematically allowed, the theory would be more predictive. It could say, in effect, that this is the hidden geometry and therefore this is the particle world that follows. But string theory has not behaved that way. Instead, physicists have found many possible ways to compactify the extra dimensions. The number of possible solutions appears extremely large, though the exact count depends on the class being considered. This abundance later becomes part of what is called the landscape problem. At this stage, the landscape does not need to be solved. It only needs to be noticed. A theory that allows hidden geometry to determine visible physics must also explain why the hidden geometry has the form it does. Without that explanation, the theory may describe a vast library of possible worlds rather than a single, unavoidable world. The power of geometry comes with the burden of selection. The texture of the idea is patient and intricate. A small folded surface may contain paths that cannot be seen from outside. A grain may look smooth until its structure is examined closely. A knot may hold information in the way it winds, even before anything is tied to it. Hidden geometry in string theory works with a similar kind of inward detail. What matters is not only that extra dimensions exist, but how they are curled, connected, and constrained. The mathematics of compactification also helps explain why string theory can sound so distant from experiment. A particle accelerator does not directly display a Calabi-Yau manifold. A detector does not take a picture of a compact dimension. Instead, experiments measure particles, forces, scattering rates, masses, and interactions. To connect string theory to observation, physicists must pass from hidden geometry to predicted low-energy physics, then compare that prediction with the world. That path is difficult. The shape of the compact dimensions influences the spectrum of particles. It can affect symmetries, coupling strengths, and the types of fields that appear in 4 dimensions. But many details must be chosen, stabilized, or derived. The theory must explain not only that compactification is possible, but why a particular compactification should correspond to the universe that exists. This is where mathematical beauty stops being enough by itself. Xingtung-Yao's work mattered because it gave physicists real mathematical spaces to use, not merely pictures. Calabi had made a conjecture about certain spaces with special curvature properties. Yau proved the conjecture in the 1970s, and those spaces later became central in string compactification. This is a useful reminder that string theory has always depended on mathematics that was not invented only for physics. Sometimes a mathematical result waits in one field until another field discovers it has become necessary. For someone trying to understand the theory simply, the safest summary is this: string theory often needs extra dimensions. Since those dimensions are not visible at ordinary scales, they are treated as compact. The shape of the compact dimensions affects the possible string states. Those states appear, from our lower energy viewpoint, as particles and forces. Therefore, hidden shape can influence visible physics. That summary is simple, but the consequences are not. The moment hidden geometry becomes part of particle identity, physics gains a new kind of explanation and a new kind of uncertainty. Perhaps the universe looks the way it does because the compact dimensions have a certain structure. Perhaps there are many structures, and the theory must explain why one is chosen. Perhaps some structures are mathematically possible but physically unstable. Each possibility carries the question further. The theory is also careful about scale. Nothing in this chapter means that ordinary space is secretly full of visible folded shapes. A person does not bump into a Calabi-Yau manifold while walking across a room. The compact dimensions, if they are part of nature at all, would be woven into the deepest mathematical structure of space. Their presence would be inferred through physics, not encountered as scenery. This distinction keeps the subject grounded. Extra dimensions are not fantasy locations. Compactification is not a hiding place for ordinary objects. Calabi-Yau manifolds are not illustrated caves inside the universe. They are mathematical candidates for the hidden geometry required by certain versions of string theory. Their importance lies in what they allow the theory to calculate, constrain, and connect. From here, string theory begins to return to the problem that first made it so interesting. Extra dimensions and hidden shapes help explain how the theory might produce particles, but the deeper promise was always tied to gravity. If the same framework that describes string states also contains a gravity-like particle, then perhaps gravity can be written in the same language as the other forces. Chapter 7: Gravity in the same language. Gravity is the oldest familiar force and the hardest one to fit into the smallest picture. A stone falls. A planet orbits. A galaxy holds together across distances so large that light itself needs thousands or millions of years to cross them. In ordinary life, gravity feels simple because it is always present. steady enough to be ignored until something moves against it. In theoretical physics, it becomes difficult precisely because it is so deeply woven into spacetime itself. Einstein's theory had changed gravity from a pull into geometry. Matter and energy shaped spacetime, and objects followed the paths that this curved spacetime allowed. That description worked with unusual power. It explained the motion of Mercury better than Newton's theory. It predicted the bending of light around massive objects. It gave physics the language of black holes, expanding universes, gravitational waves, and time passing differently in different gravitational fields. Quantum theory spoke differently. It described nature through fields, probabilities, particles, and interactions. The electromagnetic force could be treated quantum mechanically. The weak and strong nuclear forces could also be handled through quantum field theory. In those theories, forces were associated with quantum particles, photons for electromagnetism, gluons for the strong force, and W and Z bosons for the weak force. Gravity seemed to ask for something similar, a quantum particle called the graviton. The graviton is not a particle that has been detected directly. It is a theoretical expectation that appears when physicists ask what a quantum version of gravity might contain. If gravity has waves, and if quantum theory turns waves into particle-like quanta, then gravitational waves should have quantum units. In a simple description, those units would be gravitons. They would be massless, carry spin 2, and interact far too weakly to be detected one by one with present technology. A problem appears when gravity is treated like the other forces. Point-particle quantum field theory can handle many difficult infinities by a process called renormalization. The infinities are not ignored. They are reorganized so that finite predictions can be made for measurable quantities. With gravity, this method fails in the ordinary version. At extremely high energies or tiny distances, the calculations lose their predictive control. Gravity does not behave like a force that can be added cleanly to the old particle framework. The reason is tied to what gravity is. In general relativity, gravity is not merely something happening inside spacetime. It is the behavior of spacetime. Quantum mechanics, meanwhile, usually assumes some background stage on which fields fluctuate and particles interact. If the stage itself must become quantum, then the distinction between actor and theater begins to blur. A quantum theory of gravity has to describe not only things moving through space, but the quantum behavior of space and time. This is why black holes become so important. Far from a black hole, gravity can be described with general relativity. Matter near the horizon may still be treated with ordinary fields under many conditions, but the deeper questions press toward a region where curvature becomes extreme and quantum effects cannot be neglected. Black holes ask what happens when gravity compresses information, heat, entropy, and spacetime into one problem. They do not allow the two languages of physics to remain politely apart. The earliest universe creates the same pressure from another direction. In the hot, dense beginning described by modern cosmology, the universe was once far smaller, hotter, and more compressed than it is now. General relativity can trace the expansion backward to extremely early times, while quantum theory governs the behavior of matter and radiation at high energies. At the very first scales, if the extrapolation is pushed far enough, both languages are needed. Neither alone can be trusted to give the complete picture. String theory entered this problem through an unexpected route. It had not begun as a theory of gravity. Its early purpose was connected to the strong interaction and hadron scattering. Yet the mathematics of closed strings contained something that looked like the particle gravity would require, a massless spin 2 state. For a theory meant to describe hadrons, this was awkward. For a theory of quantum gravity, it was exactly the kind of feature one would want to find. Joel Scherk and John Schwartz recognized the importance of this in the 1970s. Along with related work by Tomoyuki Yoniya, they argued that the gravity-like state should not be treated as a mistake. It might be a sign that string theory had been assigned the wrong job. Instead of using it mainly as a theory of the strong force, physicists could understand it as a possible quantum theory including gravity. The unwanted particle became the central clue. The change required a shift in scale. If string theory was to describe hadrons, the strings had to have a size associated with the strong force. If it was to describe gravity, the string scale had to be far smaller, closer to the Planck scale. That made direct observation much harder, but it also placed the theory exactly where the conflict between relativity and quantum mechanics was expected to become severe. The theory moved from the laboratory scale of hadrons into the hidden scale of quantum gravity. A point particle gives interactions an unforgiving sharpness. When two point-like objects interact at a point, the calculation can force too much behavior into no distance at all. A string spreads the interaction over a tiny length and over a little two-dimensional history called a world sheet. This does not make the mathematics easy, but it changes the nature of the short-distance problem. The interaction is no longer concentrated into a single dimensionless point in quite the same way. The effect can be felt as a change in pressure. A sharp point bears everything at one location. A small surface spreads contact. A line spreads it differently again. In string theory, the spreading is not a mechanical cushion in ordinary space, but a mathematical softening at very small distances. The theory replaces point-like interaction with extended interaction, and that extension changes how ultraviolet divergences appear. This softening is one reason string theory became so attractive as a candidate for quantum gravity. It seemed to offer a framework in which gravity appeared naturally, and some of the worst short-distance infinities were controlled by the extended nature of strings. The theory did not have to bolt gravity onto a pre-existing particle list. Closed strings already carried the gravitational ingredient. The language of particles and the language of gravity could, at least within the theory, begin from the same object. Yet, careful wording matters. String theory has not been proven to be the quantum theory of gravity in nature. It has not produced direct experimental evidence showing that spacetime is built from strings. Its strength is different. It gives physicists a mathematically rich framework where quantum mechanics and gravity can be studied together without immediately collapsing into contradiction. That is a powerful reason for exploration, not the same thing as confirmation. The graviton-like state remains central to the story. In a closed string spectrum, one of the allowed states behaves like a massless spin-2 particle. General principles connect such a particle with gravity. This means that if closed strings are present in the theory, gravity is difficult to avoid. A theory that includes closed strings tends to include gravity as part of its structure. That is why string theory is often described not merely as a particle theory, but as a framework that naturally contains gravity. This also changes the meaning of unification. In many dreams of physics, unification meant placing the known forces into one elegant pattern. Electromagnetism and the weak force had already been joined in the electro-weak theory. The strong force belonged to the standard model through quantum chromodynamics. Gravity remained outside. String theory offered a different possibility, not just adding gravity to the list, but finding a basic description in which gravity and particle behavior arise from different states of the same underlying system. The price remained high. To make the theory consistent, extra dimensions entered. To include matter particles properly, supersymmetry became important. To connect the theory to the observed world, Compactification had to be chosen and controlled. Every gain opened another question. The theory's ability to speak about gravity did not remove its difficulty. It relocated the difficulty into the structure required for the speech to make sense. For a beginner, the chapter can rest on one clear idea. Gravity is hard to quantize because it is not just another force sitting inside spacetime. It is tied to spacetime's shape. String theory became important because closed strings naturally contain a state with the properties expected of a graviton, and because extended strings soften some of the short-distance problems that trouble point particle gravity. Those two facts made string theory a serious candidate language for quantum gravity. The next part of that language is supersymmetry. It is often introduced as though it were another layer of confusion placed on top of strings, but it entered for specific reasons. It helped the theory include matter more naturally, remove certain unwanted features, and connect two broad families of particles that ordinary physics treats separately. To understand why string theory became superstring theory, the missing partner has to be introduced carefully. Chapter 8: Supersymmetry, the missing partner. Supersymmetry often sounds like one more difficult word added to an already difficult theory. String theory already asks for tiny one-dimensional objects, extra dimensions, hidden shapes, and a new way to think about gravity. Then supersymmetry enters and appears to double the confusion. But its first idea is not as hard as the name makes it seem. Physics divides known particles into two broad families. One family is made of matter particles called fermions. Electrons are fermions. Quarks are fermions. These are the particles that build atoms and the material structures around them. The other family is made of force-carrying particles called bosons. Photons are bosons. Gluons are bosons. The W and Z particles are bosons. The Higgs boson belongs to this family as well. The difference between fermions and bosons is not a matter of size or importance. It comes from spin, a quantum property that has no perfect everyday picture. Fermions have half-integer spin, bosons have integer spin. That small technical difference has large consequences. Fermions obey one set of quantum rules, and bosons obey another. Matter gets its structure partly because fermions cannot all collapse into the same state. Forces work partly because bosons can gather and mediate interactions in ways fermions cannot. Supersymmetry proposes a relationship between these two families. It says that, at a deeper level, every fermion may have a bosonic partner, and every boson may have a fermionic partner. The electron would have a partner particle. The quark would have partner particles. The photon, gluon, and other bosons would also have partners. These partners are not known particles in the standard model. They are proposed particles that would appear if supersymmetry is part of nature. This is the first point to keep clear. Supersymmetry is not the same thing as string theory. It is a broader idea in theoretical physics. Some theories use supersymmetry without being string theories. Some discussions of physics beyond the standard model use supersymmetry for reasons that are not only string theoretic, but superstring theory, the physically more promising form of string theory, depends on supersymmetry in an important way. Early string theory had problems. The original bosonic string theory had only bosons. It did not naturally include fermions, which are necessary for matter particles such as electrons and quarks. It also contained an unstable feature called a tachyon, a sign that the vacuum of the theory was not physically acceptable in the simple form being considered. A theory of nature cannot leave ordinary matter outside its basic structure. It also cannot rest on an unstable foundation without explanation. Supersymmetry helped address these difficulties. By extending the theory so that fermions and bosons were related, physicists could build string theories that included matter-like particles more naturally. The unwanted tachyon could be removed in consistent superstring theories. The mathematics became more controlled. The theory began to look less like a clever model from hadron physics and more like a possible framework for all fundamental particles and forces. A useful way to hold the idea is through balance, though not as a poetic claim. Supersymmetry balances two kinds of quantum behavior. Fermions and bosons contribute differently to calculations. Under the right conditions, their contributions can cancel certain troublesome terms. This can make a theory better behaved at high energies. The partner particles are not added for decoration. They help the mathematical structure hold together. In string theory, the need for this balance appears on the string itself. A string has a surface swept out through spacetime as it moves, called its worldsheet. The mathematics on that worldsheet can include a form of supersymmetry relating bosonic and fermionic degrees of freedom. When this is done in the right way, the resulting theory becomes a superstring theory. It is more restrictive, more physically useful, and more closely connected to known matter than the older bosonic version. There is a quiet discipline in this. The theory does not simply say, let every particle have a partner because symmetry sounds elegant. It says that certain versions of the mathematics become consistent only when such relationships are present. Symmetry, in physics, is not mere visual neatness. It is a rule about what can change while the essential structure remains the same. Supersymmetry is one such rule, relating particles that otherwise seem to belong to different families. Still, the moment supersymmetry touches the real world, a question appears. If every known particle has a partner, where are the partners? The electron's partner has not been found. The photon's partner has not been found. The quark partners have not appeared in experiments. The Large Hadron Collider has searched for many possible supersymmetric particles, and so far no confirmed superpartner has emerged. This does not automatically destroy every supersymmetric theory. If supersymmetry exists in nature, it may be broken, meaning the partner particles are much heavier than the known particles. A heavy partner would require more energy to produce, perhaps more than current experiments can reach. But the absence of evidence matters. It means supersymmetry remains unconfirmed. It remains a powerful theoretical idea, not an observed feature of the particle world. The word broken can be misleading. A broken symmetry in physics does not always mean something has failed. It often means the underlying rules may have a symmetry that the visible state of the world does not show directly. A simple system can obey symmetric laws while settling into a state that does not display all those symmetries. In supersymmetry, breaking would explain why the known particles and their proposed partners do not have the same mass. Without breaking, a superpartner of the electron would be as light and visible as the electron itself. That is not what experiments see. Therefore, if supersymmetry exists, it cannot be exact at ordinary energies. It must be hidden or broken in a way that raises the masses of the partner particles. This adds another layer of difficulty. A theory must not only propose supersymmetry, it must explain how supersymmetry is broken and why the resulting particle masses look the way they do. In the history of string theory, one event made supersymmetry feel especially important. In 1984, Michael Green and John Schwartz showed that a serious mathematical problem called an anomaly could cancel in certain superstring theories. An anomaly in this context is not just an unusual result, it is a breakdown of a symmetry that the theory needs in order to remain consistent. If the anomaly stays, the theory fails. If it cancels, the theory survives an essential test. The Green-Schwartz anomaly cancellation was a turning point. It showed that certain 10-dimensional superstring theories were not merely interesting, they were mathematically consistent in a way that many physicists had not expected. The result helped begin what became known as the first superstring revolution. Researchers who had ignored or doubted string theory began to study it seriously. The field expanded quickly. That moment should not be exaggerated into proof of nature. The cancellation showed consistency inside the theory. It did not show that the universe is made of strings, but consistency is not a small thing in theoretical physics. A theory that collapses under its own symmetries cannot describe the world. A theory that survives such tests earns further attention, even before experiment can reach the scales where its deepest claims might be tested. Supersymmetry also helped connect string theory to attempts at unifying forces. In many high-energy theories, the strengths of the electromagnetic, weak and strong interactions change with energy. Supersymmetric extensions can make these strengths appear to approach one another more neatly at very high energy. This does not prove supersymmetry, but it gave physicists another reason to explore it. The same idea seemed to help several problems at once. The difficulty is that theoretical usefulness and experimental confirmation are different things. Supersymmetry can make equations behave better. It can help superstring theory include matter. It can improve certain unification patterns. It can protect some quantities from becoming unstable under quantum corrections. Yet none of those strengths is the same as seeing a superpartner in a detector. Until such evidence appears, supersymmetry remains possible, not established. For a beginner, the cleanest summary is this: fermions are matter-like particles. Bosons are force-like particles. Supersymmetry proposes that each has a partner from the other family. Superstring theory uses this relationship to build a more consistent and physically promising version of string theory. The partner particles have not been found, so supersymmetry remains hypothetical. The absence of superpartners is one of the reasons string theory can feel suspended between depth and distance. It has internal reasons for needing supersymmetry. Experiments have not yet confirmed supersymmetry in nature. The theory therefore carries a structure that may be essential to its mathematics but invisible so far in the world. That tension is not a side issue. It is part of the honest status of the subject. Supersymmetry also prepares the way for the next expansion of the theory. Once strings are placed inside a richer mathematical framework, they are no longer the only extended objects that matter. Open strings can have endpoints. Those endpoints need somewhere to live. Higher dimensional surfaces begin to enter the story, not as fantasy planes, but as physical objects in the theory's mathematics. These objects are called branes. They widen string theory beyond the image of tiny loops and strands, and they help explain why the theory eventually became larger than its own name. Chapter 9. Branes and the surfaces that hold strings. A string is already more than a point. It has one dimension of extension, even if that extension is unimaginably small. But once string theory grew into superstring theory, physicists found that strings were not the only extended objects the mathematics wanted to include. There could also be surfaces, volumes, and higher dimensional objects, each with its own role inside the theory. These objects are called branes. The word comes from membrane, but in physics it became more general than a two-dimensional surface. A membrane has two spatial dimensions, like the surface of a sheet. A string has one, a point has zero. A brane can have many possible dimensionalities. A zero brane is point-like. A one brane is string-like. A two brane is membrane-like. A three brane has three spatial dimensions, and higher branes continue the pattern in the mathematical framework. The first useful idea is simple. A brane is an extended object in string theory, just as a string is an extended object. The difference is dimensionality. A string stretches in one spatial direction. A brane may stretch in two, three, or more. It is not necessarily a surface floating somewhere like a visible sheet. It is part of the theory's description of what kinds of objects can exist in higher dimensional spacetime. At first, this can feel like the theory is becoming less simple. It began by replacing point particles with strings. Now it seems to add even larger objects. But the addition did not happen as decoration. Branes entered because the mathematics of strings led there. In particular, open strings created a question that had to be answered carefully. What happens to their endpoints? A closed string has no ends. It forms a loop and returns into itself. An open string has two endpoints, and endpoints can obey different rules. In certain versions of string theory, the endpoints of open strings are not free to wander anywhere they like through all dimensions. they can be restricted to lie on a brane. Such a brane is called a D-brane, where the D refers to Dirichlet boundary conditions, a mathematical way of saying that the endpoint position is fixed in certain directions. The term boundary condition sounds dry, but it carries the heart of the idea. A physical system often needs rules at its edges. A vibrating string on an instrument behaves differently if its ends are fixed than if they are loose. A wave in a box behaves differently depending on what is allowed at the walls. In string theory, an open string's endpoints also need rules, and D-branes provide one kind of rule. They are places where open strings can end. This changes the role of branes immediately. They are not passive backgrounds. They carry physical importance because open strings attached to them can give rise to particles and forces. If open strings end on a brane, then the excitations of those strings may appear to observers on the brane as gauge particles or matter-like states, depending on the setup. The brane becomes a stage for certain kinds of physics. The surface has its own quiet firmness in the theory. An endpoint does not drift through every hidden direction. It rests on a permitted object. Motion along the brane may be allowed, while motion away from it may be restricted. The difference between along and away begins to matter. A brane is not just another item in a list. It defines where certain strings can live and how their states are seen. Joseph Polchinski played a central role in showing how important D-branes really were. In 1995, he identified D-branes as physical objects carrying charges known as Raymond charges. This made them far more than mathematical boundary conditions. They were real objects inside the theory's own structure, with tension, charge, and dynamical behavior. After Polchinski's work, branes became central to the second superstring revolution. This was a major shift. Before then, many physicists thought of string theory mainly in terms of strings moving through higher dimensional spacetime. After D-branes became central, the theory contained a wider population of extended objects. Strings could end on branes. Branes could interact. Black holes could be described in terms of brane configurations. Dualities between different string theories could be understood more clearly. The theory had become larger than the name string theory suggested. For a beginner, D-branes can be understood through one clean sentence. They are extended objects on which open strings can end. That sentence does not explain everything, but it keeps the picture stable. Once an open string endpoint is tied to a brane, the possible motions and vibrations of the string are shaped by that brane. The physics seen by an observer associated with the brane may then arise from those open string states. This idea also allowed new ways to think about our own world. Some models suggested that the ordinary particles and forces of the standard model might be associated with open strings ending on a three-dimensional brane. In such a picture, the familiar universe could be like a three-brane embedded in a larger, higher dimensional space. Gravity, carried by closed strings, might move more freely through the larger space, while other forces remain tied to the brane. This should be held carefully. These brane world ideas are theoretical models, not confirmed descriptions of reality. They do not mean the universe is proven to be a membrane floating in a higher dimensional bulk. They show that string theory permits such possibilities and that physicists can ask whether they lead to testable consequences. Some models, including those associated with Lisa Randall and Raman Sundram, explored whether extra dimensions could influence gravity at small scales or high energies. The distinction between open and closed strings becomes especially important here. Open strings can have endpoints attached to branes, so their effects may be confined to the brane. Closed strings have no endpoints, so they are not attached in the same way. Because the graviton arises from closed string states, gravity may be able to move through dimensions that other forces cannot access in certain models. This gives a possible explanation for why gravity appears so weak compared with other forces, though no such model has been confirmed as the final account of nature. Branes also changed the study of black holes. In general relativity, a black hole is described through mass, spin, charge, horizon area, and spacetime geometry. In thermodynamics, black holes have entropy, a measure connected with the number of microscopic states that could produce the same large-scale condition. String theory using branes offered ways to count microscopic configurations for certain special black holes. This became one of the theory's most concrete successes, especially in the work of Andrew Strominger and Qumran Vafa. The link to black holes matters because it touches the meeting point of gravity, quantum theory, and information. A black hole is gravitational, but entropy is statistical and quantum in spirit. If brane configurations can reproduce black hole entropy in specific cases, then string theory is doing something non-trivial. It is not merely naming a hidden object, it is giving a microscopic account that matches a gravitational result for carefully chosen systems. Branes also helped clarify dualities. A duality is a relationship between two descriptions that look different but describe the same physics. String theory developed many such relationships, and branes often made them visible. A strongly coupled theory in one description might correspond to a weakly coupled theory in another. A brane in one version might appear as a different object in another version. This made physicists suspect that the 5 known superstring theories were not separate final theories, but different limits of a deeper structure. This is why branes became essential to the theory's growth in the 1990s. They were not optional scenery. They helped connect theories, explain non-perturbative effects, describe black hole microstates, and give open strings a physical place to end. A subject that had once seemed to be about tiny vibrating one-dimensional strings now required a broader family of extended objects. The name remains string theory, but the architecture had widened. There is a small irony in that widening. String theory became more powerful by becoming less literally about strings alone. The original replacement of points with strings opened the first door, branes opened another. They allowed the theory to describe surfaces and higher dimensional objects that carried charge, supported strings, and reshaped the meaning of spacetime in the framework. Each extension made the theory richer, while also making it harder to explain in one sentence. For someone encountering the subject slowly, the lesson can remain grounded. A brane is an extended object. A D-brane is a special kind of brane where open strings can end. Open strings attached to branes can produce particle-like states tied to those branes. Closed strings, including the gravity-like modes, are not attached in the same way. This difference lets string theory explore worlds where some physics is confined while gravity moves more broadly. None of this confirms string theory as nature's final description. It gives the framework more structure and more ways to connect gravity, particles, and geometry. Branes explain why the theory's name is partly misleading. Strings remain central, but they are not alone. The theory contains a deeper web of extended objects, and those objects become necessary when the mathematics is followed far enough. The next step is to see how this widened theory began to unify its own scattered forms. For years, physicists seem to have not one string theory, but 5 consistent superstring theories. Branes and dualities helped reveal that these 5 might not be rivals after all. They might be different views of a single larger structure. Chapter 10. 5 Theories Becoming One. For a long time, string theory had an awkward problem inside its own success. It was not one theory, it seemed to be several. Physicists had found different consistent versions of superstring theory, each with its own structure, its own allowed strings, and its own mathematical personality. A theory that had been attractive partly because it promised unity appeared, at first, to have multiplied itself. There were 5 main superstring theories. They were called Type 1, Type 1I, Type 1IB, heterotic SO32, and heterotic E8-E8. The names are not important for a first understanding, and they do not need to be memorized. What matters is the situation they created. Instead of one clean candidate for a deeper description of particles and gravity, theoretical physics seemed to have 5 related candidates. This did not mean physicists had made 5 random guesses. Each version had its own internal consistency. Some included open strings and closed strings. Some contained only closed strings. Some treated left-moving and right-moving parts of strings differently. Some carried gauge structures that looked promising for connecting to particle physics. Each version solved certain problems in its own way. The difficulty was not that the theories were careless. The difficulty was that there were too many serious ones. At first, this looked like a weakness. A final theory of nature should not seem undecided between 5 different mathematical worlds. If string theory was supposed to give physics a single deep language, why did it speak in 5 dialects? The question was especially sharp because the theories lived in 10 spacetime dimensions and already required compactification to resemble the observed world. Before even choosing the hidden geometry, physicists had to ask which string theory they were using. Then an unexpected kind of relationship began to appear. Different string theories, which had seemed separate, could sometimes describe the same physics when viewed from different limits. A theory that looked strongly interacting in one description could be related to a weakly interacting theory in another. A compact dimension that looked small in one description could correspond to a large dimension in another. A particle in one language could appear as a brane or another extended object in a different language. These relationships are called dualities. A duality does not mean that one theory is fake and the other is real. It means that 2 different descriptions may be mathematically equivalent, even though they look unlike each other. The same physical content can be written in 2 languages. One language may be easier when a certain quantity is small. The other may be easier when that quantity is large. A simple example can be stated without entering string theory fully. Sometimes one description of a system becomes difficult exactly where another becomes easy. A mountain path may be unreadable from ground level but clear on a map. A map may lose the texture of the path but reveal the route. Neither description is the mountain itself. Each gives access to features the other hides. In physics, a duality is much stronger than this comparison because it can be an exact mathematical equivalence rather than a loose change in viewpoint. One important string theory duality is called T-duality. It appears when a dimension is compact, such as a circle. In ordinary thinking, a small circle and a large circle should be plainly different, but string theory contains both momentum modes and winding modes. A string can move around a compact dimension, and it can also wrap around it. Under T-duality, a theory on a circle of 1 radius can be equivalent to a theory on a circle with an inverse radius, with momentum and winding exchanging roles. Very small and very large can mirror each other in a way point particles do not allow. This is one of the places where strings behave differently from points. A point particle can move around a compact dimension, but it cannot wrap around it because it has no length. A string can. That ability gives string theory extra structure. The compact dimension is not only a place to move through, it is also something the string can wind around. The hidden geometry becomes readable through more than one kind of motion. Another important relationship is called S-duality. It connects strong and weak coupling. Coupling measures in a broad sense how strongly objects interact. When coupling is weak, calculations may be manageable because interactions can be treated as small corrections. When coupling is strong, the same calculation can become extremely difficult. S-duality can relate a strongly coupled theory to a weakly coupled one, allowing physicists to study a hard regime through an easier partner description. This was a deep change in the way string theorists thought. Earlier methods often depended on perturbation theory, where interactions are treated as small and calculations are built step by step, but not every important physical question lives in a weakly interacting world. Branes helped open the non-perturbative side of the theory, the side not accessible by small corrections alone. Duality showed that what looked impossible in one formulation might become tractable in another. During the mid-1990s, these clues came together with unusual force. Edward Witten, speaking at a conference in 1995, argued that the 5 10-dimensional superstring theories should be understood as different limits of a single, larger framework. This framework became known as M-theory. The name has never had one universally fixed meaning. It has been associated with membrane, mystery, mother, matrix, and other playful interpretations. But the safest statement is simpler. M-theory is the proposed deeper structure whose different limits produce the known superstring theories. M-theory brought in 11 spacetime dimensions rather than 10. This was not an arbitrary increase. One of the 10-dimensional string theories, type 1IA, seemed at strong coupling to grow an extra dimension. As the coupling changed, the theory behaved as though an 11th dimension opened in the mathematical description. The theory that had looked 10-dimensional in one limit became 11-dimensional in another. Again, this should not be read as a physical doorway opening somewhere in ordinary space. It is a change in the structure of the theory. At weak coupling, one description works. At strong coupling, another description becomes more natural. The extra dimension is part of that deeper description. What had looked like 5 theories began to look like different surfaces of one larger object, each visible under different conditions. Branes became essential in this unification. In M-theory, 2-dimensional membranes and 5-dimensional branes play central roles. The theory is no longer built only from one-dimensional strings. Strings can appear as limits or special cases of higher-dimensional objects. This is another reason the name string theory remains useful historically but incomplete descriptively. The subject had grown beyond its first image. The shift from 5 theories to one larger framework changed the emotional shape of the field. Before dualities, multiplicity had looked like a problem of too many choices. After dualities, multiplicity began to look like evidence of hidden unity. The 5 theories were not necessarily rivals. They could be different approximations, each valid in a certain corner of a larger map. The fact that they connected at all suggested that the structure beneath them was not accidental. This does not mean M-theory is fully known. In fact, one of the difficult truths about the subject is that M-theory is not understood in a complete final form. Physicists know many of its limits, relationships, and special cases. They know that it connects to 11-dimensional supergravity at low energies. They know that branes play a major role. They know that it organizes the 5 superstring theories in a powerful way. But a single complete definition of M-theory, valid in all settings, remains elusive. For a beginner, this may feel strange. How can physicists speak of a theory they do not fully possess? But this happens often at the frontier. A coastline can be mapped in pieces before the full continent is understood. A mathematical object can reveal several projections before its complete structure is known. In M-theory, the known pieces fit together strongly enough to suggest a larger whole, even while the whole has not been written in one finished language. The story also shows why string theory became so mathematical. It was not only trying to describe particles, it was discovering relationships between entire frameworks. A calculation in one theory could be translated into another. A small radius could correspond to a large one. Strong coupling could correspond to weak coupling. A string could become related to a brane. These relationships were not decorative connections. They altered what physicists meant by the theory itself. Duality also changes the idea of what is fundamental. If 2 descriptions are exactly equivalent, then choosing one as the real description and the other as merely a trick may not be meaningful. The string in one picture, the brane in another, the geometry in a third, and the field theory in a fourth, may all be ways of reaching the same underlying physics. The deeper structure may not look exactly like any one of them. This is part of why string theory can be hard to explain simply. Its beginner image is a tiny vibrating string. Its advanced form often becomes a network of dual descriptions, higher dimensional objects, compact shapes, and quantum gravity relations. The beginner image is not false, but it is incomplete. It is the first doorway into a subject that later teaches physicists to distrust any single doorway as final. The 5 theories problem, then, did not disappear by choosing a winner. It changed through connection. Type 1, Type 1IA, Type 1IB, and the 2 heterotic theories became linked by dualities. M-theory appeared as a proposed deeper structure behind them. branes became central objects rather than side features, the theory's unity became less like a single sentence and more like a set of exact relationships between descriptions. There is still a cost, a framework that contains many limits, many compactifications, and many branes becomes difficult to connect uniquely to experiment. Unity at the high level does not automatically produce one clear prediction at accessible energies. The theory can become more coherent mathematically while also becoming harder to test directly. That tension will return later when the landscape and experiments enter the story. For now, the essential lesson is narrower. String theory once seemed to come in 5 separate versions. Dualities showed that these versions are deeply connected. M-theory proposed that they are different limits of a larger 11-dimensional framework. The subject did not become simpler in its details, but it became more unified in structure. Once physicists had learned that one theory could hide behind several descriptions, another idea became easier to approach. Perhaps gravity itself could have more than one description. Perhaps a theory with gravity in one space could be equivalent to a theory without gravity on a boundary. This was the turn that brought string theory into one of its most influential modern ideas, holography. Chapter 11. Maldacena and the holographic turn. The duality teaches physics to be careful about appearances. 2 descriptions can look unlike each other and still carry the same physical content. One may speak in the language of strings, another may speak in the language of fields. One may seem to live in a higher dimensional space, another may seem to live on a lower dimensional boundary. The difference can be so large that the mind wants to choose one as real and the other as a clever shadow. But the mathematics can sometimes refuse that choice. This is the ground on which holography entered string theory. The word holography can mislead because it brings to mind projected images, science fiction rooms, or illusions made of light. In theoretical physics, the word has a stricter meaning. It suggests that all the information describing a region with gravity may be encoded on a lower dimensional boundary. The idea is not that the world is fake, it is that gravity may admit an equivalent description in fewer dimensions. The roots of this idea reached into black hole physics before string theory gave it its most famous form. Jacob Bekenstein had argued in the 1970s that black holes carry entropy, and Stephen Hawking later showed that black holes radiate thermally when quantum effects are included near the horizon. Black hole entropy was proportional not to the volume inside the black hole, but to the area of its event horizon. That was a strange clue. In ordinary systems, entropy often grows with volume. In black holes, the horizon area carried the count. Gerard Hooft and Leonard Susskind later developed the holographic principle from this kind of reasoning. If the maximum information in a region is related to the area of its boundary rather than the volume inside it, then perhaps a theory with gravity has a deep lower dimensional description. The idea remained broad and suggestive. It needed a precise example, a place where the sentence could become mathematics rather than only a guiding thought. In 1997, Juan Maldacena proposed such an example. His work connected a theory of gravity in a particular kind of spacetime with a quantum field theory living on its boundary. The full name, anti-de Sitter transformal field theory correspondence, is usually shortened to AD-SCFT. The name is heavy, but its first meaning can be stated gently. A gravitational theory in one setting may be equivalent to a non-gravitational quantum theory on the edge of that setting. Anti-de Sitter space is not the spacetime of the everyday universe. It is a mathematically useful spacetime with constant negative curvature and a boundary structure that can be handled in precise ways. A conformal field theory is a quantum field theory with special symmetry under changes of scale. Those definitions are enough for a first pass. The important point is not that our universe literally is anti-de Sitter space. The important point is that Maldacena gave physicists a concrete case where gravity and a lower dimensional quantum field theory appeared to be 2 descriptions of the same thing. The boundary carries unexpected weight in this idea. A region with gravity has depth, bulk, and interior geometry. The field theory on the boundary has no gravity in the same sense, and one fewer spatial dimension, yet the two are related so closely that calculations in one description can correspond to calculations in the other. What looks like geometry and gravity on one side can look like quantum fields without gravity on the other. A surface can hold more than it seems to hold. The boundary is not a painted shell around an empty center. In the correspondence, it contains the information needed to describe the gravitational bulk. The word contains should be understood mathematically, not as storage in a box. Operators, states, temperatures, fields, and geometries are related through a dictionary between the two sides. The bulk and boundary are not separate universes talking loosely across a wall. They are two languages for one structure. This was powerful because gravity is often difficult. Quantum gravity in the bulk can be hard to calculate directly. A related quantum field theory on the boundary may sometimes be easier to handle. The correspondence gave physicists a way to translate gravitational questions into field theory questions, and field theory questions into gravitational ones. It did not solve every problem, but it opened a new working method. The turn was also conceptually unsettling in a controlled way. Usually, people think of space as the container and fields as things inside it. Holography suggested that in some settings, space and gravity in the interior may emerge from degrees of freedom described on the boundary. The interior is not dismissed as unreal. Instead, its reality may be encoded in a different form. The depth of space becomes something that a lower dimensional theory can reproduce. Maldaceno's proposal quickly became one of the most influential papers in theoretical physics. Stephen Gubser, Igor Klebanov, and Alexander Polyakov developed one formulation of the correspondence, and Edward Witten clarified major parts of its structure. The result was not a single isolated insight, but a framework that many physicists could use. String theory, quantum field theory, black holes, nuclear physics, condensed matter models, and mathematical physics all began to draw from the same correspondence in different ways. For someone learning string theory simply, the reason ADS/SLIFT matters can be kept narrow. It is a clear example of duality involving gravity. On one side is a string or gravity theory in a higher dimensional space. On the other side is a quantum field theory without gravity on the boundary. The two sides look different, but the correspondence says they describe the same physics. That is why it is often called gauge-gravity duality. The word gauge points back to the kind of theories used in the Standard Model, where forces arise from symmetries. Electromagnetism, the weak force, and the strong force are all described through gauge theories. The conformal field theory is a special kind of quantum field theory, but the broader lesson is that a field theory resembling the language of particle physics can be related to a theory containing gravity. This link brought string theory closer to fields it had once seemed separate from. Black holes gained new meaning through this relationship. A black hole in the gravitational bulk can correspond to a thermal state in the boundary field theory. Temperature, entropy, and information can be studied from both sides. Questions that once seemed trapped inside the horizon problem could sometimes be translated into the language of ordinary quantum systems. The information problem did not vanish, but the correspondence made it harder to treat gravity and quantum mechanics as permanently incompatible. There is a careful limit. ADS/EFT is best understood in settings different from the observed large-scale universe. Our universe appears to have a small positive cosmological constant, closer to de Sitter-like behavior than anti-de Sitter behavior. This means Maldaceno's correspondence is not a direct statement that the everyday cosmos is exactly described by that original model. It is a precise laboratory for quantum gravity, not a finished map of all reality. That distinction matters because string theory often gives physicists model worlds where deep questions become calculable. A model world can teach real physics even when it is not identical to the observed universe. In ADS/CFT, the value lies in the exactness and usefulness of the relationship. It shows that a theory with gravity can be equivalent to a theory without gravity in a lower dimensional setting. That is enough to change how physicists think about spacetime. The correspondence also reshaped the idea of emergence. In ordinary speech, Emergence means that large patterns arise from smaller parts. A wave emerges from many water molecules. Temperature emerges from molecular motion. In holographic duality, geometry itself may be emergent from quantum degrees of freedom. Distances in the bulk may be related to patterns of entanglement in the boundary theory. The shape of space begins to look less like a fixed starting point and more like a consequence of quantum structure. This connects back to the original problem of quantum gravity. General relativity treats spacetime as the main actor in gravity. Quantum field theory usually treats spacetime as the stage. Holography suggests that, at least in some settings, spacetime geometry may be reconstructed from a non-gravitational quantum theory. The stage may be written in the language of the actors. That is why the idea reached far beyond string theory itself. Still, AD/EFT remains difficult. The simplest statement hides many layers. The gravitational side can involve strings, branes, black holes, and curved higher dimensional geometry. The field theory side can involve strongly coupled quantum systems where ordinary calculation is hard. The dictionary between the two sides is rich, but not always easy to use. Simplicity at the level of concept does not remove complexity at the level of work. For the beginner, the stable version is this. Holography in physics means that the information of a gravitational region may be encoded on a lower dimensional boundary. Maldacena gave a precise version of this idea through AD/EFT. The correspondence relates a gravity theory in a bulk spacetime to a quantum field theory on the boundary. It is not a claim that reality is an illusion. It is a claim that two very different mathematical descriptions can be equivalent. This is why Chapter 11 belongs after dualities. Without duality, holography sounds almost impossible. With duality, it becomes another, deeper example of the same lesson. Physics may allow more than one language for the same structure. What appears as curved space and gravity in one language may appear as quantum fields and boundary information in another. The subject becomes less about choosing the one picture the mind finds comfortable, and more about understanding the translations. AD/CFT also changed string theory's reputation. Even physicists, skeptical that string theory has been confirmed as the final theory of nature, often use ideas that came from it. Holography became a tool, a way of thinking, and a bridge between fields. A theory can remain unconfirmed as a complete description of the universe, while still producing methods that reshape physics. That is one of the unusual positions string theory now occupies. The next confusion grows from a different kind of abundance. Dualities suggested unity behind 5 theories. Holography suggested equivalence between gravity and boundary fields, but compactification still allowed many possible low-energy worlds. If hidden dimensions can take many shapes, and if those shapes lead to different physics, then string theory may not point to one universe in a simple way. It may point to an enormous landscape of possibilities. Chapter 12. The Landscape Problem. The landscape problem begins with an uncomfortable abundance. Earlier chapters followed string theory toward unity. Point particles became strings. Strings required extra dimensions. Extra dimensions gained hidden shape. 5 theories became connected through dualities, and holography showed that gravity itself might have more than one description, but another direction in the theory did not narrow so neatly. When physicists asked what the hidden dimensions could look like, the answer did not seem to be one shape. It seemed to be many. That is the first simple version of the landscape problem. String theory does not give only one obvious way to turn 10-dimensional or 11-dimensional mathematics into the 4-dimensional world people observe. The extra dimensions can be compactified in many possible ways. Different shapes, different fields, and different hidden arrangements can lead to different low-energy physics. Instead of one road leading straight to the known universe, the theory appears to contain a vast range of possible roads. This matters because a physical theory is not only judged by how much it can contain, it is also judged by what it can select. A theory that allows everything explains too little. A theory that allows many possible worlds must also explain why this world has the particles, forces, masses, and constants that it has. The landscape problem is the problem of selection. If many solutions are possible, why is our solution the one that nature uses? The word landscape is useful because it suggests a field of possible valleys, peaks, and resting places. In physics, these resting places are often called vacua. A vacuum here does not mean empty space in the everyday sense. It means a possible stable or semi-stable state of the theory, a background arrangement in which fields and dimensions settle into a particular configuration. Different vacua can produce different apparent laws at low energies. This is one of the places where ordinary language becomes risky. A vacuum sounds like nothing, but in quantum field theory and string theory, a vacuum can have structure, fields can have values, hidden dimensions can have shapes, fluxes can thread cycles in the compact space, symmetries can be broken in different ways. What looks like emptiness at ordinary scale may depend on a deep arrangement that decides what kinds of particles and forces appear. A compactified string theory does not merely hide 6 dimensions and then stop. Those dimensions must be stabilized. Their sizes and shapes must be fixed, or at least made stable enough that the visible world does not change wildly. If a hidden dimension could freely expand, shrink, or distort, the physics built from it would change as well. Particle masses, force strengths, and other quantities might drift. The observed world is stable enough that any deeper geometry must be controlled. Flux compactification became one way physicists studied this control. A flux, in this context, is a field threading through part of the compact geometry. The details are mathematical, but the broad idea is manageable. Hidden fields can wrap through hidden cycles, helping stabilize the shape and size of compact dimensions. Different choices of flux can lead to different vacua. The theory gains many possible stable or semi-stable arrangements. The surface of the idea is quiet, but the consequences are large. A hidden shape may have cycles that fields can thread. A field choice may help hold part of the geometry in place. A stabilized geometry may produce one set of particles and constants rather than another. Nothing in this chain is visible directly to a detector as a little folded object. The detector sees only the low-energy result. The hidden arrangement remains behind the measured world. As physicists studied these possibilities, the number of possible string vacua appeared extremely large. A number often associated with the landscape is 10 to the power of 500, though it should be treated as an estimate from certain classes of constructions, not as a single exact count of all possible realities. Its role is not to give a tidy statistic. Its role is to show the scale of the problem. The theory may allow a number of possible low-energy solutions so large that ordinary selection becomes difficult. For some physicists, this abundance looked like a crisis. A theory of fundamental physics had been hoped to predict the properties of the universe from deep principles. If string theory allowed enormous numbers of possible vacua, perhaps it could not predict why the electron has its mass, why the forces have their strengths, or why the cosmological constant is small but not zero. The theory might explain how many worlds could be mathematically possible without explaining why this one was necessary. For others, the landscape looked less like failure and more like a clue. Perhaps the laws observed in one region of reality are partly environmental, shaped by which vacuum that region occupies. If many vacua exist in the theory, and if cosmology can populate different vacua in different regions, then the observed constants might be conditioned by where observers can exist. This line of thinking leads toward anthropic reasoning, especially in discussions of the cosmological constant. Anthropic reasoning must be handled with care. At its most restrained, it says that observations are filtered by the conditions necessary for observers to exist. A universe with constants that prevented atoms, stars, chemistry, or long-lived structures would not contain observers asking why the constants are what they are. This does not automatically solve the problem. It changes the kind of explanation being offered. Instead of deriving one unique universe, it explains why observed conditions might fall within a life-permitting range. Many physicists remain uncomfortable with that move. The discomfort is understandable. Physics has often advanced by finding necessary structures beneath apparent accidents. The hope was not merely to say that the universe allows observers. but to derive why its laws take their precise form. If the landscape replaces prediction with selection effects, some see that as weakening the theory's scientific force. Others see it as an honest response to what the mathematics seems to allow. Leonard Susskind became one of the well-known defenders of the landscape viewpoint. He argued that the large number of string vacua might help explain the small observed value of the cosmological constant, especially when combined with anthropic selection. The cosmological constant is connected to the energy of empty space and the accelerated expansion of the universe. Its observed value is tiny compared with many naive theoretical expectations. The landscape of many possible values might make a small positive value less surprising. The difficulty is that less surprising is not the same as precisely predicted. A landscape can make room for the observed value, but making room is weaker than deriving it uniquely. This distinction runs through the debate. String theory may contain vacua that resemble important features of our world. The harder task is to show that the theory selects our vacuum, or at least makes strong testable predictions about it. Qumran Vafa and others developed a different response, known as the swampland program. The name draws a contrast between the landscape and the swampland. The landscape contains low-energy theories that can arise consistently from quantum gravity. The swampland contains low-energy theories that may look acceptable by ordinary field theory standards but cannot be completed into a consistent theory of quantum gravity. The goal is to find criteria separating the two. This is an important shift. Instead of asking only how many possible string vacua exist, the swampland program asks what kinds of effective theories quantum gravity permits at all. If sharp criteria can be found, then quantum gravity may rule out many theories that seemed possible. The landscape would still be large, but its edges would become meaningful. The theory would gain predictive power by saying not only what may exist, but what cannot. The swampland idea remains active and debated. Some proposed criteria are supported by many examples. Others are uncertain. Because the subject sits near the frontier, it must be described as a research program, not as a completed map. Its value lies in trying to turn the abundance of possibilities into constraints. It is a search for boundaries in a space that can otherwise feel too wide. For a beginner, the landscape and swampland can be held together in one calm picture. The landscape is the set of possible low-energy worlds string theory may allow through different compactifications and choices. The swampland is the set of theories that may seem possible from a low-energy view but fail when quantum gravity is demanded. The landscape asks why our vacuum was chosen. The swampland asks which apparent choices were never truly allowed. The landscape problem also explains why string theory is hard to discuss in simple slogans. The phrase theory of everything suggests a single final equation from which the observed world drops out cleanly. The real situation is less tidy. String theory may provide a deep framework containing gravity, particles, branes, and geometry, yet still face a major challenge in connecting that framework uniquely to the known universe. Its depth and its difficulty are not separate facts. They come from the same richness. A hidden geometry can produce visible physics. That idea once sounded like a source of elegant explanation. It still may be. But if hidden geometries are numerous, then elegance turns into a selection problem. Which geometry? Which fluxes? Which vacuum? Which mechanism stabilizes it? Which low-energy particles appear? Which constants follow? Each answer leads to another layer that must be fixed before the theory touches experiment. This is why the landscape problem is not just philosophical. It affects prediction. If string theory can produce many worlds with different low-energy physics, then an experimental result may be hard to identify as uniquely string theoretic. A discovered particle, symmetry, or extra-dimensional signal might support some string-inspired models, but the framework's flexibility can make clean confirmation difficult. The theory must find ways to say something sharp enough that nature can answer. Still, the abundance is not the same as emptiness. A large solution space can contain structure. Mathematicians and physicists study how vacua are distributed, which compactifications are stable, which low-energy theories are ruled out. and which features recur across broad classes of models. Patterns inside the landscape may matter even if one unique vacuum has not been derived. The problem is not that nothing can be learned. The problem is that learning must proceed through a very wide space. The listener can hold the chapter's core idea in plain words. String theory may allow many possible hidden arrangements. Each arrangement can lead to different visible physics. That creates a problem for prediction, because a theory must explain why our world has the laws it has. The landscape names the abundance. The swampland names the attempt to find the limits. From here, the next question becomes anaerobic. If string theory allows strings too small to see directly, dimensions too hidden to move through, and many possible vacua to choose among, how can it be tested? Physics does not live by mathematical possibility alone. At some point, the theory must meet instruments, measurements, and the stubborn silence of things not yet found. Chapter 13. Why experiments have not found it. The hardest question around string theory is not whether its ideas are beautiful, deep, or mathematically useful. The hardest question is whether nature has given any sign that the theory describes the real world. Physics can begin in mathematics, but it cannot remain only there forever. A theory about the universe must eventually face measurement, even if the measurement is indirect, delayed, or difficult. String theory faces this question under difficult conditions. If the fundamental strings are associated with the Planck scale, then they are far smaller than anything present experiments can directly resolve. The Planck length is about 10 to the minus 35 meters. A proton is already extremely small, around 10 to the minus 15 meters across. The gap between those scales is not a small technical inconvenience. It is a gulf of 20 orders of magnitude. Particle accelerators do not see by using ordinary light. They probe small distances by using high energies. The higher the energy, the smaller the distance scale that can be examined. The Large Hadron Collider is the most powerful particle accelerator yet built, and it has reached energies of several trillion electron volts in proton collisions. That is enormous by human engineering standards. It is still far below the Planck energy, where the simplest versions of string-scale physics are often expected to live. This is the first plain reason experiments have not found strings. The objects, if they exist at that scale, are too small to be seen directly with present instruments. A detector would not show a tiny loop or strand. It would show ordinary particle events, tracks, energy deposits, missing momentum, decay products, and statistical patterns. To connect such events to strings, physicists would need signs that the deeper framework leaves a measurable trace. The situation is not unique to string theory. Many parts of modern physics are inferred rather than seen in a simple visual way. Quarks are not isolated and photographed one by one. Neutrinos are detected through rare interactions. Gravitational waves were measured through tiny changes in the lengths of interferometer arms. A theory may be tested through consequences rather than direct images. The problem for string theory is that its cleanest consequences often sit at energies too high or forms too flexible for straightforward tests. One possible route was supersymmetry. Many string theories rely on supersymmetry, and supersymmetry can also appear in particle physics models beyond the standard model. If superpartner particles had been found at collider energies, that would not have proved string theory by itself, but it would have strengthened a structure that many string models use. It would have showed that nature contains a symmetry long expected in superstring frameworks. So far, that has not happened. Experiments at the Large Hadron Collider have searched for many possible supersymmetric particles, including partners of quarks, gluons, and electroweak particles. No confirmed superpartner has appeared. This does not rule out all supersymmetry because the partner particles may be heavier than current experiments can produce, or arranged in ways that are harder to detect, but it does remove the simplest hope that low-energy supersymmetry would appear quickly. That silence matters. A detector's silence is not empty. It narrows possibilities. It pushes some models into higher energy ranges. It makes certain simple versions less attractive. It forces theorists to reconsider assumptions about where supersymmetry might be broken and how visible its partners should be. Absence is not the same as disproof, but in experimental physics it is still information. Extra dimensions offered another possible path. If extra spatial dimensions were larger than the tiniest compact dimensions usually imagined in early string theory, they might affect gravity or particle collisions at accessible scales. Some models proposed that gravity could spread into extra dimensions while other forces remained confined to a brane. In such cases, experiments might look for deviations from Newton's law at short distances, missing energy in collider events, or new resonances connected to higher dimensional physics. No confirmed signal of large extra dimensions has been found. Precision tests of gravity at small distances have continued to support the known behavior down to very short scales. Collider searches have not produced agreed evidence for extra-dimensional particles or missing energy patterns that require such models. As with supersymmetry, this does not eliminate every possible extra-dimensional construction. It does mean that the more accessible versions have not been confirmed. The instruments have pressed against the theory from more than one side. Colliders search through high-energy particle events. Tabletop experiments test gravity at small distances. Cosmological observations look for traces in the early universe. Gravitational wave astronomy opens another kind of listening, not to strings themselves in the fundamental sense, but to possible cosmic defects or early universe processes that some theories might allow. Each method touches a different edge of the question. Cosmic strings are one possible observational idea, though they should not be confused automatically with fundamental strings. In cosmology, a cosmic string is a long, thin topological defect that might have formed during phase transitions in the early universe. Some string theory models can produce objects that behave like cosmic strings on cosmic scales. If such objects existed, they might leave gravitational effects, lensing signatures, or gravitational wave signals. Searches have placed limits, but no confirmed cosmic string detection has established string theory. Another possible clue lies in the cosmic microwave background, the leftover radiation from the early universe. Certain high-energy theories can leave patterns in primordial fluctuations, gravitational waves, or non-Gaussian features. String-inspired inflation models have been studied in this context. Yet the early universe is not a simple laboratory. Many different theories can produce similar broad effects, and observations must be interpreted with care. No current cosmological pattern has singled out string theory as the necessary explanation. Black holes provide a more theoretical testing ground. String theory has had real success in counting microscopic states for certain special black holes and reproducing the Bekenstein-Hawking entropy formula. This is not a collider experiment. It is a mathematical match between a quantum counting problem and a gravitational thermodynamic result. It gives support to the idea that string theory can describe aspects of quantum gravity. It does not prove that every black hole in nature is fully described by the specific string construction used in the calculation. ADS-CFT offers another kind of evidence. Though evidence may not be the right word in the experimental sense, it is a precise theoretical relationship, supported by many checks, between certain gravitational theories and certain quantum field theories. It has become one of the strongest reasons physicists continue to take string theory seriously. But ADS-CFT is not a direct measurement of strings in the universe. It shows that string theory contains powerful, consistent examples of quantum gravity. It does not by itself show that our universe is one of those examples. This distinction is central. String theory has theoretical evidence of consistency and usefulness. It has mathematical successes. It has links to black hole entropy, gauge theory, geometry, and quantum information. But direct experimental confirmation of fundamental strings, compact extra dimensions, supersymmetric partners, or a uniquely string-derived standard model has not arrived. The honest status sits between dismissal and certainty. Some critics argue that this distance from experiment is too great. A theory that cannot make accessible, unique predictions may begin to drift away from the ordinary discipline of physics. If many compactifications are possible, and if the string scale is unreachable, then almost any experimental result might be accommodated after the fact. This is the worry. Not merely that string theory is hard to test, but that it may be too flexible to be tested sharply. Supporters answer in several ways. They point out that frontier theories often develop mathematically before experiments catch up. General relativity predicted effects before some of them could be measured precisely. Gravitational waves took a century to detect after Einstein's theory. They also note that string theory has generated tools useful beyond its original goal, especially through holography and dualities. Even without direct confirmation as the final theory, it has produced physics that would not easily have appeared elsewhere. Both sides are responding to real facts. The theory has not been experimentally confirmed as nature's final framework. The theory has also not been empty. It has produced deep internal consistency checks, unexpected mathematical relationships, and concrete calculations in quantum gravity settings. The question is not whether string theory is obviously true or obviously worthless. The question is whether its path toward physical confirmation is strong enough. A fair view has to keep several layers separate. The standard model is experimentally established to high precision in its domain. General relativity is experimentally established in its domain. Supersymmetry is not confirmed. Extra dimensions are not confirmed. Fundamental strings are not confirmed. M-theory is not known in complete final form. ADAS-CFT is a powerful theoretical correspondence in specific settings. Black hole entropy calculations in string theory are serious achievements, but they are not direct observations of strings. This layered view may feel less satisfying than a yes or no answer, but it is more accurate. Science often contains regions with different degrees of certainty. Some parts are measured, some are inferred, some are mathematically compelled inside a framework, some are speculative extensions. String theory crosses several of these regions at once. That is why conversations about it can sound confused unless the layers are kept apart. The experimental problem also explains why string theory has many different reputations. To some physicists, it is the most developed candidate framework for quantum gravity and unification. To others, it is a beautiful but overextended mathematical structure that has not delivered the predictions once hoped for. To still others, it is valuable mainly as a source of tools, even if its original ambition remains unfulfilled. Each view selects a different part of the record. For a beginner, the cleanest answer is this. Experiments have not found string theory because the most direct string scale is likely far beyond current reach, and the more accessible signs, such as supersymmetry or large extra dimensions, have not been confirmed. The theory remains studied because it gives a coherent way to combine gravity and quantum mechanics, contains powerful dualities, and has produced useful results in black hole physics and quantum field theory. This is not a failure that can be dismissed in one sentence. It is also not a victory that can be declared in one sentence. String theory stands in a long middle region. Its mathematics reaches farther than experiment. Its physical claims remain unconfirmed. Its tools continue to work in places that matter. Its deepest promise remains open. A detector waits for events. A telescope gathers old light. An interferometer measures a shift smaller than a proton's width. Instruments do not care whether a theory is elegant. They answer only in traces, limits, patterns, and silence. So far, string theory has received many limits and much silence from the experimental world, but not the decisive signal that would turn it from candidate framework into established description. That silence leads into the final question. If string theory has not been found directly, and if its largest claims remain unconfirmed, why does it still matter? The answer cannot be that it has solved everything. It has not. The answer lies in what the theory has given physics, even while remaining unfinished. Chapter 14. What string theory still gives physics? String theory has not delivered the simple ending people once hoped for. It has not produced a direct image of a string. It has not given a single unavoidable compactification that leads cleanly to the standard model. It has not shown experimental proof of supersymmetry. large extra dimensions, or the full hidden architecture its mathematics allows. If the question is whether string theory has been confirmed as the final theory of nature, the careful answer is no. But an unfinished theory can still change physics. That is the position string theory occupies. It stands between achievement and uncertainty, between mathematical structure and experimental distance. Its largest physical claim remains unconfirmed, yet many of its tools, ideas, and connections have become part of modern theoretical physics. It has not closed the search for quantum gravity. It has helped define what that search must take seriously. The first gift was a new way to include gravity in a quantum framework. In ordinary point-particle quantum field theory, gravity becomes difficult at very high energies. The calculations lose predictive control. String theory changed the smallest object from a point into an extended one, and in doing so changed the short-distance behavior of the theory. Even more importantly, closed strings naturally contained a massless spin-2 state, the kind expected for the graviton. Gravity appeared from inside the framework rather than being attached afterward. That fact still matters. It does not prove that nature uses strings, but it shows that a theory of extended quantum objects can contain gravity in a controlled way. For physicists trying to understand black holes, the early universe, and the meeting point of spacetime with quantum mechanics, such a framework is valuable. It gives the problem a language. It gives calculations a place to begin. Black holes are one of the clearest places where string theory gave physics something concrete. In the 1970s, Jacob Bekenstein and Stephen Hawking had shown that black holes behave thermodynamically. They have entropy, they radiate. Their entropy is proportional to the area of the event horizon. This raised a deep question. If entropy counts microscopic states, then what microscopic states does a black hole have? General relativity could describe the large-scale black hole geometry. It could give the horizon area. It could tell how space-time curves. But by itself it did not count the hidden quantum states responsible for the entropy. A microscopic explanation required a quantum theory of gravity. String theory offered such an explanation in special cases. In 1996, Andrew Strominger and Kumran Vafa counted microscopic states for a certain class of supersymmetric black holes using D-branes in string theory. Their calculation reproduced the Bekenstein-Hawking entropy formula for those black holes. This was not a direct observation of strings in a telescope. It was a mathematical match between a quantum count and a gravitational thermodynamic result. For string theorists, it became one of the strongest signs that the framework was capturing something real about quantum gravity. The importance of the calculation lies in its precision. A black hole's entropy, from the gravitational side, depends on its horizon area. The brane calculation counted the number of microscopic arrangements that could produce the same large-scale object. The two answers matched in the cases studied. That kind of agreement does not settle every question, but it is not a vague resemblance. It is a structural contact between quantum states and curved spacetime. The result also showed why branes mattered. They were not decorative additions to strings. They could carry charge, form bound states, and produce black hole-like systems whose microscopic states could be counted. The theory had widened beyond one-dimensional strings because the physics required more. Branes made certain quantum gravity questions calculable in a way that had not been available before. Adsley CFT became another major contribution. Maldasena's correspondence gave physics a precise example where a theory with gravity in a higher dimensional bulk could be equivalent to a quantum field theory without gravity on a lower dimensional boundary. This changed how many physicists thought about spacetime. Gravity in that setting could be translated into a non-gravitational language. Geometry could be related to quantum information. A difficult bulk problem could sometimes be studied through boundary fields. This was more than a string theory curiosity. Holographic methods began to influence the study of black holes, strongly coupled quantum systems, nuclear matter, condensed matter models, and quantum information. Not every application is a direct claim about the real universe. Many are controlled model problems. But model problems can teach. They allow physicists to see how gravity, entropy, temperature, and quantum entanglement may fit together in ways that ordinary methods obscure. A theory can be useful before it is final. This is not special pleading for string theory. It is a common feature of science and mathematics. A framework may reveal relationships, produce tools, or open calculations that remain valuable even while its largest interpretation stays unsettled. String theory has done this repeatedly through dualities, branes, compact geometry, mirror symmetry, and holographic correspondence. Duality may be one of its deepest habits. String theory taught physicists that two descriptions which look different can be physically equivalent. A small, compact dimension can correspond to a large one. A strongly coupled theory can correspond to a weakly coupled theory. A gravitational theory can correspond to a non-gravitational theory. These are not merely changes of wording. They are exact or highly controlled relationships that allow difficult questions to be moved into easier forms. This affects the meaning of understanding. In older pictures, understanding often meant finding the one correct set of objects and equations. String theory complicated that hope. It suggested that the same physics may appear through several languages, none of which alone deserves to be called the final image. A string description, a brane description, a field theory description, and a geometric description may each reveal one side of a structure that exceeds them. The mathematics has also traveled beyond its original physical ambition. Mirror symmetry, which emerged from string theory, connected different Calabi-Yau spaces in surprising ways and gave mathematicians new tools for solving problems in enumerative geometry. Ideas from string compactification influenced algebraic geometry and topology. The flow was not one-directional. Mathematics gave string theory many of its shapes, and string theory returned unexpected mathematical predictions. This exchange is one reason the subject remains alive. Even when the physical interpretation is debated, the mathematical structure continues to produce relationships that can be checked inside mathematics itself. A physicist may ask whether strings exist in nature. A mathematician may ask what the theory reveals about geometry. These are different questions, and string theory has affected both. Still, the unresolved problems must remain in view. String theory has not yet selected a unique vacuum corresponding to our universe. It has not explained with certainty why the constants of nature take their observed values. It has not shown why the compact dimensions, if they exist, have one particular shape rather than another. It has not given experimentally verified superpartners. It has not turned the landscape into a sharp predictive machine. The theory also faces the problem of accessibility. If the most direct string effects live near the Planck scale, then ordinary experiments may never reach them directly. Physicists may have to rely on indirect clues, consistency arguments, cosmological traces, black hole physics, or mathematical necessity. That is not impossible, but it is harder than the path taken by many earlier theories. The farther a theory sits from measurement, the more carefully its claims must be handled. This is why string theory should not be spoken of as settled truth. It should also not be dismissed as empty because it has not yet produced a single decisive experiment. The honest position is quieter. It is a candidate framework for quantum gravity and unification. It is an unfinished mathematical structure with many known limits and many unknowns. It has produced important tools. It has left major physical questions unanswered. For someone who has never heard of string theory before, the whole subject can now be held in a simpler order. Physics first had point particles and fields. Gravity did not fit comfortably into the quantum picture. String theory replaced points with tiny extended objects. Different string states could appear as different particles. Closed strings naturally included a gravity-like state. Consistency pushed the theory toward extra dimensions, supersymmetry, compact geometry, branes, dualities, and holography. Then the same richness created the landscape problem and made experimental confirmation difficult. That order removes some of the confusion. Extra dimensions do not appear because physicists wanted mystery. They appear because the mathematics demands more structure. Branes do not appear because strings were abandoned. They appear because open strings, dualities, and non-perturbative physics require higher dimensional objects. Holography does not mean reality is fake. It means gravity in one setting may have an equivalent lower dimensional description. The landscape does not mean anything goes. It means the theory contains many possible solutions. and selection becomes a serious problem. The final value of string theory may not be known for a long time. It may become part of a confirmed theory of quantum gravity. It may be replaced by something deeper that keeps some of its structures and discards others. It may remain a vast mathematical framework whose tools survive even if its original ambition changes. Science has room for all three possibilities, because theories often leave behind more than their first promises. There is a calm discipline in leaving the answer unfinished. Physics does not become weaker when it admits what is not yet known. It becomes clearer. String theory has given physics a way to think about gravity and quantum mechanics together. It has given black holes microscopic counts in special cases. It has given dualities that connect distant descriptions. It has given holography, branes, and new mathematical bridges. It has also given physics a reminder that depth and confirmation are not the same thing. At the edge of the subject, no final verdict waits in a simple sentence. There are equations still being studied, compact spaces still being classified, quantum systems still being compared across dual descriptions, and experiments still narrowing the space of what nature allows. The theory remains open, not as a finished answer hidden behind difficulty, but as a working structure whose meaning is still being tested by mathematics, consistency, and whatever evidence the physical world may one day provide. Beyond the debate, ordinary physics continues with its steady reliability. Electrons still fill atomic shells. Photons still carry light across rooms and between stars. Gravity still shapes falling bodies, planetary paths, and the slow motion of galaxies. The Standard Model still describes the particles already measured, and general relativity still describes spacetime across the ranges where it has been tested. String theory lives beneath those familiar successes as a possible deeper language, not yet confirmed, not yet dismissed. It asks whether the point was ever the final beginning. It asks whether geometry, particles, and gravity may be different surfaces of one structure. It asks whether what looks separate at ordinary scales may become connected at scales no instrument has reached. The answer remains beyond direct touch. For now, matter keeps its forms. Light crosses the distance it is given. Gravity continues to curve the paths of bodies and the ticking of clocks. Fields fluctuate in ways instruments can measure, and particles appear in detectors as brief marks of energy and charge. Beneath those marks, the smallest description remains unwitnessed, held in mathematics, constrained by what is known, and waiting at the edge of what can be tested. The journey is complete. Rest well.